Good morning, everyone. I think audio and video is clear. I'm fine, Raghuram, thank you. So tell me, guys, is audio video clear? Okay, so I think we should start now. So let's start the session, guys. In the previous class, because this is the second class, in the previous class I told you about the basics of power electronics, and I told you some topic. Let me revise those things so that those students who have not watched the previous session, they can get the information of which topic I have covered in the previous class, and then we'll start with the new topic today. So this is my introduction, and let me tell you guys, from 17th onward, from 17th of January, there is Master MSQ series is going to start, because MSQ play a very important role. So that's why we are going to start this MSQ series. So it will start from 17th of January, and I hope you will enjoy this series. Okay, and one more thing is one open mega mock test is there for GATE 2023 student. You can register yourself. The link is given in the description, so you can go there and you can register yourself. And one more mega workshop is also there for GATE 2024 students. You can recommend your juniors, your friends who are preparing for 2024, and this session is taken by Abhinav Negi sir on 15th of January. So please recommend them. There is one session, general aptitude, so it is also going to start, and Rakesh Taleja sir will take this session. So general aptitude is for 15 marks. I hope you can score 15 out of 15. So join this session also. The date will be announced soon. Okay. For mathematics, marathon session is again, it will be coming soon, and it will be taken by Rakesh sir and Ankit Joshi sir. So you can also attend this session, because this is again very important. Okay, now you can join the test series for your GATE exam, and BYJU'S exam prep is also providing you the test series. So you can join the test series. The test series is very, you can say, it's according to the GATE exam, and 60 plus tests are there, including the mock test and the subject wise test, and the virtual calculator is there, and 4,000 plus practice questions are there. I mean, there is so much practice, so you can join this test series, guys, and you can get benefited from it. Okay, those students who have not subscribed our channel, please subscribe it and press the bell icon and hit the like button, so that you can get the notification. If you press the bell icon, you'll get the notification whenever the class will be live. You will be notified. So in the previous class we have covered this AC transient. First we have covered, and then we have taken some question on AC transient, and then we have covered with the basics of power electronics, like input power factor, okay, and how to calculate the active power. I told you about that, Parseval relation, okay, and then I told you about the about some questions. We have taken some questions on this input power factor, okay, and then I told you about the quarter wave symmetry, why this quarter wave symmetry is important. So in the previous class I covered that part also. Next, I told you about the distortion and the total harmonic distortion. Okay, what is the meaning of total harmonic distortion? What is the meaning of displacement factor and the current distortion factor? I told you this topic in the previous class. Is it fine now? Okay. Is it clear? Okay, internet may create the problem, guys, so don't lose your patience, because whenever it is buffering, I'll revise it, I'll repeat the topic, so don't lose your patience. Okay, so it might be possible that in between the class there is some interruption due to internet. Okay, because in the last class also we have faced the same problem. So don't lose your hope and don't lose your patience. Be with the class, and I hope you will learn some new things. So in the previous class, I told you about the effect of source inductance in this diode circuit, okay? And then I told you if you have an inductive load and half wave controlled rectifier is there, then how to analyze. I told you about the properties of inductor, okay? Whenever you have inductor, then how can you draw these waves without any calculation, okay? So I told you about that, and then I told you about this circuit, and then we have solved for RL circuit in half wave controlled rectifier, okay? And then RL circuit with freewheeling diode, half controlled rectifier with RL circuit and freewheeling diode. So I told you about this also. And then LE load, I told you about LE load, okay? I also told you about now we entered into this again effect of source inductance with thyristor. Previously we have 2 diodes, now we have 1 thyristor. So I covered this topic, okay? And now we are going to start with the full wave controlled rectifier. So in full wave controlled rectifier, there are so many loads like R load, L load, RL load, RLE load. So what I'm going to do is, I'm going to cover only RL load and RLE load. Why? Because if you have covered RL load and RLE load, in RL load, if you make R equal to 0, you will get L load. If you get L equal to 0, you will get R load. Or most probably, say, if you ask me accurately, I should teach you about RLE load. Because in RLE load, if you make E equal to 0, it will become RL load. If you make R equal to 0, it will become LE load. If you make L equal to 0, it will become RE load. And if you take E equal to 0, it will become RL. I mean, every type of load you can analyze from it, okay? So I will more focus on 2 type of load. One is RL, one is RLE, okay? We will cover only these 2 topics, and then we'll proceed. We'll understand the effect of source inductance then, okay? So three things I am going to tell you in single phase full controlled rectifier. One is RL load, and one is RLE load, and one is effect of source inductance, okay? So let's start the class, guys. Let's start with this RL load. So what I have is, I have this RL load, and this is a full wave controlled rectifier. In this rectifier, I want to analyze this output voltage. What will be the output voltage? And I want to analyze the average current, average output current, I naught T. What is the average value of this I naught T? I want to analyze this, okay? So now how to analyze that? What you can do is, let's say the firing angle is alpha. So T1, T2 will get fired together, and T3, T4 will get fired together, okay? So remember this point. And I also told you one more point, and that point was, I told you that whenever you have L in the load, remember one point. And what was that point? Whenever you have L in the load, then in that case, once the current is developed, then inductor will decide whether it will allow the thyristor to turn off or it will not allow the thyristor to turn off. If there is an alternate path for the current, and if the voltage become negative, then you can turn off the thyristor. What is the meaning of this? Okay, let me tell you the meaning of this, because many students are confused with this. Okay, so remember one point. Whenever L is there in the load, once the current has developed, L will decide whether to turn off the thyristor or not turn off the thyristor. Okay, I'll tell you how it is, why this inductor is, how it is doing like this. Okay, there is one more point that I told you. Whenever the load contains the resistance, in the previous class, if you remember, I told you that this current will be continuous. Whether it is continuous, the current will be periodic. Whether it is continuous or discontinuous. Okay, if the load contains R, I naught T will be periodic. I naught T will be periodic for sure. Whether it is continuous conduction or discontinuous conduction, it doesn't matter, but it will be periodic for sure. Okay, so let's try to draw the wave shape, and let's try to analyze this circuit. So let's say I'm firing at alpha. The firing angle for T1, T2 is alpha and T3, T4 is pi plus alpha. So at this instant I am firing. This is alpha. So at this instant I am firing T1, T2. So let's take this point down. This is my alpha, okay? At this instant I am firing T1 and T2. T1 and T2, okay? Now what will happen, guys? Tell me. As soon as you fire it, let's say you start from this point only. As soon as you fire T1, T2, what will happen, guys? As soon as you fire T1, T2, you can see that this will be sorted. So this positive point of the source voltage will be available at this point. And the negative point of the source voltage via this T2, it will be available here, okay? Because you can see that the source voltage will come in parallel with the load, okay? Whenever T1, T2 gets conducting, whenever T1, T2 get fired, so they will be sorted. Once they will be sorted, this supply voltage will appear across the output. So you can say that the output voltage will be equal to the supply voltage. Output voltage will be equal to the supply voltage. So at this instant alpha, output voltage will be same as the supply voltage. So let's draw it up to pi. Let's draw it up to pi. So up to pi, you can see that the output voltage shape is same as the supply voltage shape. Okay. What about the current? In RL circuit, I told you about the current. How to write the equation for the current. Let me write the equation for the current. It's an AC transient situation. It's like this situation. Let me show you. We have R and we have L. There was no initial current, and we have an AC source. So at the instant omega t equal to alpha, we have closed the switch. At the instant omega t equal to alpha, we have closed the switch, okay? Now what should be the current? So this is the situation, guys. This is the situation here. Because at omega t equal to alpha, you are firing T1, T2. It means the supply voltage is connected across the load at omega t equal to alpha. Now what I need to do is, I need to write the equation for the current. How to write the equation for the current? Now you'll ask me, sir, why you are so much interested in writing the current equation? Because the current equation will tell us whether the conduction will be continuous, discontinuous, or just continuous. That's why I'm more interested in writing the current equation. So let's write the current equation first. What is the current equation, guys? To write the current equation, I told you this is AC transient. How to write the current equation? I know T has two parts. One is I know T steady state and one is I know T transient. Now tell me, this is equal to Vm by Z sine of omega t minus theta Z. This is the steady state part. Whatever the voltage is divided by the impedance. Impedance is R plus J omega L. Okay. Now it has some magnitude, which is more Z you can write. And the angle is theta Z. Theta Z will come in the numerator and will be minus theta Z. Is it fine? This is the steady state part. Now I have to take one more current, that is transient current. At omega t equal to alpha, this is not zero. But we want this current to be zero. Why? We want this current to be zero because the initial current in the inductor was zero, no? That's why. So at omega t equal to alpha, this current is Vm by Z sine of alpha minus theta Z. At omega t equal to alpha, the steady state current is equal to this. It means it is not zero. At omega t equal to alpha, it is not zero. To make it zero, you have to subtract this. And since it is the transient current, it will decay exponentially. R by omega L. Here you have to write omega t minus alpha. I hope it is clear. So this is the output current equation. Now if you want to plot this output current equation, it will be like this. So it will start from here and it will go like this. At this pi, it will not be zero. And the current maxima will be before pi. Why it is before pi, I'll tell you. Why it is before pi, at what instant this maxima will be there. Whenever this inductor current is zero, whenever this VLT is zero, at that instant current maxima will be there. I told you in the previous class. Whenever this inductor voltage is 0, at that instant the current maxima will be there. So I'll tell you where this maxima will come, but it will come before pi, that's for sure. Okay, so this is the current equation, and at pi this current is not 0, it is some positive value. Since the current has developed in the inductor, now tell me, at pi or maybe after pi you can see that the voltage become negative, the supply voltage become negative. Does it mean that T1 T2 will get turned off? Answer is no. Why? Because T3 T4 will get fired at pi plus alpha. At pi plus alpha, T3 T4 will get fired. At pi plus alpha, T3 T4 will get fired. So up to pi plus alpha, T3 T4 are not conducting, and this current needs some path. This current needs some path. I told you, na, inductor will not let these thyristor to turn off. Why? Because there is no alternative path. There is no other path for this current. At pi, this current has developed some value. Inductor current has developed some value. Since this current has developed some value at pi, this current needs some path. And that path is not provided by T3 T4. Why? Because T3 T4 are fired at pi plus alpha. So after pi plus alpha, you can say that T3 T4 will start conducting, but before that this current has to pass from T1 T2 only. It means T1 T2 has to conduct. So even after pi, T1 T2 has to conduct. It means the output voltage will remain as the supply voltage, because this is sorted here, this is sorted here. So whatever the supply voltage is, that supply voltage will come across the output. It means the supply, whatever the supply voltage is, that will be the output voltage. And since the supply voltage is negative, so the output voltage will also be negative up to this. And the current, let's say the current is just continuous. Let's say current is becoming 0 here. Let's assume that I am taking just continuous. I am taking just continuous. I am taking just continuous situation. It means current is becoming 0 just at pi plus alpha. But it's not necessary. It's not necessary that current is always just continuous. It may be possible that the current is not 0 at pi plus alpha. It may be possible that the current becomes 0 before pi plus alpha. So there might be three possibilities here. One is just continuous. The second one is discontinuous. And the third one is continuous. Third one is continuous. So there might be three possibilities: just continuous, discontinuous, and continuous. Now let's discuss one by one, every situation one by one. First, let's discuss the discontinuous conduction. In discontinuous conduction, what will happen is this current, this inductor current, will become 0 before pi plus alpha. This current will become 0 at some beta angle. We call it extinction angle beta. It might be possible that the current becomes 0 before this pi plus alpha. It means up to pi plus alpha, up to beta T1 T2 will conduct, and from beta to pi plus alpha T1 T2 will turn off. No thyristor is conducting now. So up to beta T1 T2 are conducting. It means up to beta the output voltage will be same as the supply voltage. It means this supply voltage will be the output voltage will be equal to supply voltage only up to beta. Only up to beta. This instant is beta. Only up to beta the output voltage will be same as the supply voltage. Now from beta to pi plus alpha, output voltage will be 0. Okay, output voltage will remain 0. From beta to pi plus alpha there is no current, no thyristor is conducting, so every thyristor is off. If every thyristor is off, then the output voltage will remain at 0. And then what will happen? Then again at this position T3 T4 are fired. If T3 T4 are fired, then what will happen, guys? This negative will appear here. You can see that this negative will appear here, okay, and the positive will appear here. It means the output voltage will be opposite to the supply voltage. Now the output voltage will be negative of the supply voltage. Is it fine? Because you can see that the negative point will be available here and the positive point will be available here. So this supply voltage will come across the load like with this polarity, but the output voltage is of this polarity. So you can say that output will be opposite to the supply voltage. So at pi plus alpha, what will happen is, this is my supply voltage, you take the opposite to that. If you take the opposite to that, so it will be like this. It will be like this. Okay, and the current will start again from 0. Okay, it will start again from 0. Okay, because the current is discontinuous. Since the current is discontinuous, it means it will start from 0 again. It will start from 0 again, and at 2 pi it will be positive somewhat. Is it fine? It means at 2 pi T3 T4 will not stop conducting, because T1 T2 will get fired at 2 pi plus alpha. At this instant T1 T2 will get fired. So the current will, I mean, this current has to flow, and this current will flow through T3 T4. It means T3 T4 will continue conducting. So it means T3 T4 will keep conducting up to this instant, and up to this instant output voltage will be negative of the supply voltage. Whatever the supply voltage is, negative of that. Is it fine? Up to this instant. And then since the current has become 0 here, so from this instant to 2 pi plus alpha, from this instant to 2 pi plus alpha, the current remains 0, output voltage will also remain 0. Is it fine, guys? Output voltage will also remain 0. Now at this instant, again you fire T1 T2. So output voltage will be again supply voltage. I hope it is clear, and you can repeat the same thing. You can repeat the same thing. Is it clear, guys? So this is my discontinuous conduction. In discontinuous conduction, you will always have this beta, extinction angle. We call it extinction angle. Time of thyristor T1 T2. You can also calculate that. And there are so many things which you can calculate from beta. Okay. Is it clear now? Is it clear now? Okay. So I was telling you that this beta is important. How to calculate this beta? Tell me, guys. How to calculate this beta? Because once you get this beta, once you know this beta, then easily you can calculate many things. Many things like conduction time of the thyristor. For how much time T1 T2 will conduct this time? Beta minus alpha. You can calculate that. And I mean, there are other things also like circuit turn of time, and there are so many things, and the average output voltage. So you can calculate those things if you know this beta. Now how to calculate this beta? In calculation of the beta, this current equation will help us. How? We know that this current will be 0 at this omega t equal to beta. So what you do is, you put omega t equal to beta in this equation and make it equal to 0. This current is 0 at omega t equal to alpha because it is starting from 0, no? But it will become 0 again at omega t equal to beta. At this length, at omega t equal to beta, it is again becoming 0. So what you do is, you put omega t equal to beta in this expression and make it equal to 0. So if you do like this, it will be Vm by Z sine of beta minus theta Z minus Vm by Z sine of alpha minus theta Z e to the power minus r by omega L beta minus alpha, and make it equal to 0 and find beta. Now the problem is, you can't find beta. You can't find beta. Why? Because beta is inside the sine term and beta is in exponential term. That's why it's a non-linear equation. This is the main problem. So we will not be able to find this beta. Okay, we will not be able to find this beta, but no problem. Let's say beta is given in the question, beta is provided to you in the question. In the statement, they provide you with the beta. Once you get this beta, then you can calculate the conduction time of the thyristor, beta minus alpha. You can easily calculate that. And the second thing is, you can also calculate the average output voltage. Now tell me the average output voltage. V naught T average. You can calculate the average output voltage. How to calculate the average output? What is the period of this output voltage? Period is pi. After pi length, you can see that this alpha point will repeat at pi plus alpha. So the period is pi. So how to calculate the average value? Average value is area under one period divided by the time period. And the time period is pi. So 1 upon pi, we need to calculate the area under one period. From alpha to beta, we need to calculate the area. From alpha to beta, and the equation is Vm sin omega t. Okay? Vm sin omega t d omega t. Now you can calculate like this, Vm by pi, integration of sign is minus cos, upper limit minus lower limit, it will be cos alpha minus cos beta. This way you can calculate V0T average value. Output average value you can calculate like this. Is it fine, guys? Now you can see that in output average value you have this beta term. Once you know this beta, now if beta is provided to you, you can calculate the average output voltage, and from this average output voltage you can also calculate the average output current. Why? How? Let me tell you guys. We know that V0T is equal to VLT plus VRT, because whatever the output voltage is, it will be broken into two parts, this VRT and this VLT. And we know that if the conduction is discontinuous, it will be periodic. We know that. Even if the conduction is not discontinuous, R is there. Na? If R is there in the load, current will always be periodic. If current is periodic, what is VLT average? VLT average is 0. In the inductor, if current is periodic, VLT average will be 0. What does it mean? It means if you take average on both sides, it will be VLT average plus VRT average. VLT average is 0 always, whether the conduction is continuous, discontinuous, just continuous. Why? Because of R, because R is there. So now what you can do is you can make it equal to 0. So you can say that VRT average equal to V0T average. Now what is VRT average? VRT average is R into I0T average. So R into I0T average is equal to V0T average. VRT average equal to V0T average. So V0T average is R into I0T average. So from here I can calculate the average value of the current. I0T average came out to be V0T average value divided by R. This way you can solve it, okay? So you can calculate the average value of the current. I hope it is clear to everyone. If you know the average value of the output voltage, then you can easily solve it. I told you about this case. I told you about discontinuous conduction. Now what I want to do is I want to again solve the question for just continuous case. For discontinuous I have covered. Now let's come to just continuous. Let's see how the wave shape will look like for just continuous conduction. So what I can do is I can remove it. I can remove this shape, and I can redraw the shape. So let me redraw it in the new shape. Okay, let's make it here. Let's make it here. So actually we require 3 wave shape. So better we make all the 3. Okay, I think it's fine. Okay, we require 3 waves. So this is my supply voltage, Vm sin omega t. This peak value is Vm. Okay, this is minus Vm. Now at T1, T2, this is my pi. This instant is alpha. This instant is pi plus alpha. This instant is 2 pi plus alpha. 2 pi plus alpha. Okay. Now we are ready to understand for just continuous case. Let's say at alpha, this is my alpha instant. At alpha, you have fired T1, T2. So the output voltage will be same as the supply voltage. So at this point, output voltage will be same as the supply voltage, and it will go like this. Up to this instant pi. Up to this instant, output voltage will be same as the supply voltage, and this peak value will be Vm if you take ideal situation. So from alpha to pi, the output voltage will be same as the supply voltage, and the current will go like this. The current equation is this, and it will start from 0, and it will be some positive value at this pi. It will have some positive value at this pi. Okay, let me redraw this. So the maximum of the current will come before this pi. Okay, maximum will come before pi. Why that is true, I will tell you. So at pi it is positive. It means after pi, T1, T2 will keep on conducting. If T1, T2 will keep on conducting, then the output voltage will remain as same as the supply voltage. and the current will fall like this. Let's say the current will become 0 at pi plus alpha. Current becomes 0 at pi plus alpha. So up to pi plus alpha, output voltage will be same as the supply voltage. Okay, now at pi plus alpha, what will happen? At pi plus alpha, you have fired T3, T4. At this instant, you have fired T3, T4. If T3, T4 are fired at this instant, then the output voltage will be negative of the supply voltage. Output voltage will be negative of the supply voltage. It means you have to take negative of this. If you take the negative of this, then the output voltage will look like this. This will be my output voltage. Okay, and the current will again start from the 0 and will become 0 here. Is it fine? This way the current will look like. It means the current is just continuous. You can see that. Current is becoming just continuous. And then again at 2 pi plus alpha, T1, T2 will get fired and the output voltage will look like this. So there is no zero gap in the output voltage. You can see that. In previously, you have a 0 volt gap in discontinuous conduction. And there was an extinction angle beta. But now the extinction angle is at pi plus alpha itself. It means the conduction is just continuous. Conduction is just continuous. It is becoming 0 at pi plus alpha, and again at pi plus alpha itself, the next cycle start. So current is just continuous. Just continuous. Now the question is at what alpha the conduction will become just continuous? How to calculate that? What you do is, in this current equation, we know that this current will become 0 at beta. Previously it was 0 at beta, so we put omega t equal to beta. But in this situation, current will become 0 at pi plus alpha. So you can put omega t equal to pi plus alpha and make it equal to 0 and calculate the value of alpha. Okay? What you do is, in this current equation, you put omega t equal to alpha, pi plus alpha and make it equal to 0. If you put omega t equal to pi alpha minus theta. Tell me guys, is it clear? Okay, so it's buffering again. What we can do is, oh, why it is buffering? There is a problem with the internet. I don't know why this is creating so much problem. I think we have to replace this internet connection. Anyway, so I told you, now you can see that this is the current equation and this is the current equation, and at pi plus alpha, this is becoming 0 again. So what you do is, you put omega t equal to pi plus alpha and make it equal to 0. So what I did is, I put omega t equal to pi plus alpha. If you put omega t equal to pi plus alpha, the equation will look like this: Vm by z sine of pi plus alpha minus theta z minus Vm by z sine of alpha minus theta z e to the power minus, at this omega t, you put omega t equal to pi plus alpha. Alpha will cancel, only pi will be there. So it will become e to the power minus r pi by omega l. Is it clear guys? Is it clear? And make it equal to 0. Now what you do is, you calculate alpha from here. And you can calculate alpha must be equal to theta z. Okay, you can easily calculate that. It means if alpha is equal to impedance angle, now what is the impedance angle? Impedance angle is tan inverse of omega L by R. This is my impedance angle, theta z. If alpha is equal to this value, then the conduction will be just continuous. And the average output voltage will be V naught T average will be equal to, what is the average output voltage guys? Average output voltage will be equal to, you can take the average value of this, it will be 2 Vm by pi cos alpha. Okay? Whenever there is no zero gap in the output voltage, whenever there is no 0 volt gap in the output voltage, then the average output voltage will always be 2 Vm by pi cos alpha. Okay? You can take the average value, the period is pi, so 1 over pi, and take the area from alpha to pi plus alpha. Okay, and it will come out to be 2 Vm by pi cos alpha. This is my average output voltage. Once you get this average output voltage, divided by R will be the average output current. So we have found for this alpha equal to theta z, for this alpha equal to theta z, the conduction is just continuous. When you take alpha equal to theta z, conduction is just continuous. Now what will happen is, if you take alpha less than theta z, if you decrease the alpha from this, then conduction will become continuous. If you take alpha greater than theta z, it will become discontinuous. Just remember this point. In continuous conduction, alpha is greater than theta z. Alpha less than theta z. Excuse me. Why it is less? I will tell you why it is less. If you take alpha less than theta z, the conduction will be continuous. If you take just continuous, okay? If you take alpha equal to theta z, conduction is just continuous. Alpha greater than theta z, the conduction will be discontinuous, and alpha less than theta z, the conduction will be continuous. Why it is so? Why you are making less? Why not greater? Look at the output voltage. Look at the output voltage. If the output voltage is increasing, let's say, if it increases, obviously the output average current will also increase. Tell me guys, because we know that the output is alpha divided by R. Okay. Now you can see that whether the conduction is just continuous or continuous, output average voltage will remain same. Why? Because there is no gap. There is no gap. In continuous conduction, only the zero will not appear. The current will always be continuous. The zero will not be there in the current. Okay. In just continuous, it is becoming zero just for one moment and then it start again. So what will happen in continuous conduction? The average output voltage formula will remain same, because just continuous is a subset of continuous. Just continuous is subset of continuous. That's why the average out, then the current wave shape will come upward. Then only the average value will increase. Na? It means if it is continuous, if the current become continuous, if it is not touching the 0 point, if it is continuous, then the average value will be higher. Now tell me, when this average value will be higher, tell me guys, when you decrease the value of alpha, because it is cos alpha, it means you have to decrease the value of alpha. So if alpha is less than theta z, if alpha is less than theta z, the conduction will be continuous. If alpha is equal to theta z, the conduction will be just continuous. In both the cases, the average output voltage remains same. It is 2 Vm by pi cos alpha. And if alpha is greater than theta z, then you can say that the conduction will become discontinuous. I hope it is clear to everyone. I hope it is clear. So I told you that in RL load there are three possibilities: just continuous, discontinuous and continuous. Now let's come to the other load. Let's try to understand the other loads also. What are those other loads? What I can do is I can add one slide. Let me add one slide and then I will tell you what are those other loads. Wait. Okay. Now come to the original situation. Now we have RL load. We have RL load. We have RL load. And we know that the theta z came out to be tan inverse of omega L by R. Is it fine? Theta z came out to be tan inverse of omega L by R. Now be careful guys. What can be the possible maximum value of theta z? Can you tell me? What can be the possible maximum value of theta z? What can be the possible maximum value of theta z? If L is very high, let's take L very high, then theta z will approach 90 degree. Tell me guys, if L is very high, then theta z will approach 90 degree. It means if alpha is greater than 90 degree, conduction will be discontinuous. Conduction will be discontinuous. However high, whatever high value you take, theta z cannot be beyond 90 degree. If theta z cannot go beyond 90 degree, it means if alpha is greater than 90, so 100%, the conduction will be discontinuous. Okay, whatever L you can take infinite. it doesn't matter. You take L equal to infinite. For L equal to infinite also, theta z will become approximately 90. So if you take alpha greater than 90, there will be discontinuous conduction for sure. Remember this point. There are many books, then generally is less than 90. Okay. It was buffering. So let me repeat this. There are many books in which it is written that L is very high. Whenever the L is very high, they take continuous conduction. Now let me tell you guys, you can't take continuous conduction every time. If L is very high, even though L is very high, you can't increase alpha beyond 90 degree. If you take alpha beyond 90 degree, it will always be discontinuous. However high L you take, it doesn't matter. Whatever value of L you take L equal to infinite. Then also theta z came out to be 90 degree. It means if you take alpha greater than 90 degree, it will always be discontinuous. So you have to be careful, because in books it is written if L is very high, then conduction will be continuous. It's not like that. Continuous only if you take L. Tell me guys, is it clear? Yeah, I'm very frustrated with the internet. Every 2 minutes. Okay, wait a minute here. Yes, I understand that. It's very disturbing. Wait. So I have put the request, guys. Just wait for 5-10 minutes. I suppose it will be resolved. Just wait for 5-10 minutes, okay? Can I proceed? I think it's fine now. I think it's fine now. Okay. Okay, let's continue the class. Let's continue the class. If it happens again, then we'll take. I mean, we have to restart the modem. Okay, so okay, let's start the class now. So I told you that whenever you have RL load, and if L is very high, however high you take L, theta z will not be beyond 90 degree. It means if you take alpha greater than 90 degree, for always, the conduction will be discontinuous. Wait a minute, guys. Let me restart the modem because I think it's creating the problem. So please wait for 5-10 minutes. Okay, please wait for 5-10 minutes and let me restart the modem. Tell me, everyone, is it fine now? Please tell me. Is it fine now? Is my audio and video clear? Tell me, everyone. Is my audio and video clear? I think it's clear. Okay. Okay, let's start the session. So I told you in RL load, however high L you take, theta z will not be beyond 90 degree. What does it mean? If theta z is not beyond 90 degree, I mean theta z can be approximately 90 degree if you take L very high. Then if you take alpha greater than 90 degree, for sure conduction will be discontinuous. However high L you take, it doesn't matter. I was telling you in many books it is written that if L is very high, you take continuous conduction. And many teachers do like this. Many teachers say like this. This is not true. Okay. Why it is not true, I told you. If L is very high, then you take continuous conduction only if alpha is less than 90 degree. Otherwise, you can't take continuous conduction. Okay. I hope it is clear to everyone. Now, I told you that using RL load, we can also analyze the R load and the L load. Okay, we can analyze the R load and the L load. So let's analyze R load and the L load also. What you can do is, in this expression, let's say you take only L load. If you take L load, it means you are making R equal to 0. If R is equal to 0, now tell me, what is theta z? Theta z came out to be 90 degree. It means if alpha is less than 90 degree, conduction will be continuous. Continuous conduction. And if alpha is greater than 90 degree, conduction is discontinuous. Conduction is discontinuous. Okay, conduction is discontinuous, and alpha equal to 90 degree, conduction is just continuous. Conduction is just continuous. Fine. Because R is equal to 0, then theta z become 90 degree. Okay. If R is 0, then theta z become 90 degree. It means the load is pure L. So in pure L, alpha less than 90 degree, conduction is continuous. Alpha greater than 90, discontinuous. Alpha equal to 90, just continuous. Now tell me, in continuous conduction and in just continuous conduction, V naught T average will be equal to 2 Vm by pi cos alpha. This is my output voltage average value. Okay, for continuous conduction and for just continuous conduction, output average value is 2 Vm by pi cos alpha. Fine. Now, if you look at this carefully, if alpha is less than 90 degree, then it is positive. If alpha is less than 90 degree, then it is positive. It means the average output voltage is positive across. This average output voltage is positive. Now tell me, if average output voltage across this inductor is positive, if the average voltage across inductor is positive, it means the current is rising. In this case, the current will be continuous, but it will be rising and aperiodic. It will be rising and aperiodic. Rising and aperiodic. Okay. Why it is so? Because I told you, if alpha is less than 90 degree, then the average value across inductor is positive. If average value across inductor is positive, it means the current will keep on rising. Current will keep on rising. So current will be rising and aperiodic. Current will be aperiodic and it will keep on rising. Okay. Now you'll ask me, sir, will it be aperiodic? Yes, it will be aperiodic. Why? Because R is not there. R is not there, only L is there, and the average voltage is positive. So current in every cycle, the current will keep on rising. Now in just continuous case, average voltage is 0. So average voltage is 0. What does it mean? It means I naught T, the current will be periodic. Current will be periodic. It will be just periodic. It will be periodic and just continuous. Current will be periodic. Periodic current. Current will be periodic, guys. In this case, current will be periodic. And let me tell you, it is just continuous. Now, let's come to the discontinuous conduction. In discontinuous conduction also, current will always be periodic. In discontinuous conduction, it will always be periodic. If current through the inductor is periodic, what is the average output voltage? V naught T average in this case will be 0. You don't need to calculate beta. You don't need to calculate beta in this case. Okay, in discontinuous conduction, you don't need to calculate beta because there is pure inductor. In pure inductor, in discontinuous conduction, current is periodic. If the current is periodic, you can say that output average voltage will always be 0. Okay. If current through the inductor is periodic, the average voltage across that inductor will always be 0. So you can write like this. Is it fine? So using this RL load, I told you about the L load. Now let's come to R load only. If you take only R load, tell me guys, if you take only R load, whenever you have R in the load, current can never be rising. Current will always be periodic, whether continuous is there or discontinuous is there. Current will always be periodic. Okay. Now, what is theta Z? Theta Z becomes 0 degree. It means if alpha equal to 0, then it will be just continuous. It will be just continuous. Okay. If alpha equal to 0, because theta Z is 0, na? So if I take alpha equal to 0, the conduction is just continuous. Okay. If alpha is greater than 0, it will be discontinuous. It will be discontinuous. Okay. Remember this point. For only R load, only for alpha equal to 0, it will be just continuous. If you take alpha greater than 0, conduction will become discontinuous. Now you can see that. You can see that in this wave, let's say the load is R. In this situation, let's say the load is R. Let's take R load. This is my R load. In this R load, let's say you fire at this angle alpha. You fire at this angle alpha. So obviously from this point to pi, the output voltage will be same as the supply voltage because T1, T2 are conducting. So from alpha to pi, this will be output voltage. What about the output current? The output current will also have the same shape because R load is there. No? So whatever the voltage shape is there, divided by R will be the current shape. You can see that at this pi angle, the current has become 0. Now from pi to pi plus alpha, no thyristor will conduct. No thyristor is going to conduct. So at pi plus alpha, what will happen, guys? At pi plus alpha, T3, T4 will start conducting. At this instant, you have fired T3, T4. If T3, T4 are fired, then the output voltage will be negative of the supply voltage. Is it fine? And the current will also be like this. in this situation, voltage will never go negative. Why? If the voltage goes negative, if the voltage across this R goes negative, then the current will also go negative. And if current is negative, it means current is going like this. These thyristor will not allow the current in reverse direction. So current cannot go negative. Current cannot be negative. That's why the current has to stop at pi. Current is 0 at pi. You can see that. Current is 0 at pi. Okay, and this is pi plus alpha. This point is pi plus alpha. So I told you that in this case, if alpha is greater than 0, if you take alpha greater than 0, then the conduction will be discontinuous always. Okay, so you can analyze this. Okay, so I told you about L load when you take only L and when you take only R. I hope it is clear. In just continuous conduction, the average value will be 2 Vm by pi cos alpha, and you put alpha equal to 0. So the average value, average output voltage will be 2 Vm by pi. So if you take alpha equal to 0 in R load, if you take alpha equal to 0, then the wave shape will be this wave shape, no? Pure this wave and then pure sine wave this. Okay, this will be my output voltage for alpha equal to 0, and the average value of this wave is 2 Vm by pi. You know that. Okay, this way we can calculate the average output voltage. I hope it is clear. So for R load, it's very simple. Okay, if you take alpha greater than 0, it will be discontinuous. You can see that the current is discontinuous. There is a 0 gap. Okay, now for alpha greater than 0, what will be the average output voltage? You can calculate the average value. How to calculate the average value? Tell me, guys. Now the average output voltage will be, beta is pi always. In this R case, beta is always pi. Okay, so what you can do is you can calculate the average value. It is area under one period divided by the time period. So time period is pi, and if you look at the area will be alpha to pi Vm sin omega t d omega t. Okay, this way you can calculate the average output voltage, that is Vm by pi, integration of sine is minus cos 1 plus cos alpha. This way you can calculate V naught t average value. This is my output average value. I hope it is clear to everyone. This is my output average value. Is it fine, guys? So this way we can calculate the average output voltage. It is simple. In R load, whenever the conduction is discontinuous, in R load, this is the average output voltage. And in R load, always the conduction is discontinuous. Why? Because only for 0, it is just continuous. If you increase alpha beyond 0, it will always be discontinuous, and the average output voltage will be Vm by pi into 1 plus cos alpha. Remember this point. Okay, so I told you about this. Now let's come to, I told you about R load. Now we can also understand L load only. Okay, we can also understand L load only. Is it clear, guys? Tell me. Tell me, guys, is it clear? Is it clear? Is it fine now? I don't know why this problem is there. I think it's the backend problem. I think it's because the modem is Geo internet. I think the Geo is it's not a good internet. I mean, I think I have to change the internet connection. Okay, so let's start, guys. So I told you, if the load is pure L, what will happen? Now what I want to tell you is, there are some situations in which we replace this RL load with a constant current source. There are some situations where we replace this RL load with a constant current source. And what are those situations? We generally take it constant. Sometimes it is given in the question that is L is very high such that current is ripple free. They say L is very high such that current is ripple free. Current is ripple free. If they write like this, what does it mean? It means you have to take current constant. You have to take current constant. Current is ripple free. Ripple free means the current is constant. Now what should be the value of this current? What should be the value of this current? How much current source, what is the value of this current source? By how much value we can replace this RL load with a current source? Tell me guys, how to calculate this current source value? It's simple. Since L is very high and current is ripple free, it means current is continuous. Current is constant and continuous. If current is constant and continuous in RL load, then the output voltage will be 2 Vm by pi cos alpha. This will be my average output voltage. Tell me guys. This will be my average output voltage. So how to calculate this I naught value? I naught is a DC current, average current. So you can calculate that I naught came out to be 2 Vm by pi divided by R cos alpha. Okay, so whenever you need to replace this RL load with a constant current source, you replace with this value. You replace this current source with this value. Is it fine? Is it fine guys? So whenever L is very high, let's say it is given that L is very high and it is so much high that the current is ripple free. If the current came out to be ripple free, it means the current is constant. It means it's continuously coming and it's constant. It means the conduction is continuous. For continuous conduction, the average output voltage is 2 Vm by pi cos alpha. Divide by R, you will get the average current, and this current source has to be equal to this value. Okay, so please remember this point, because there are some situations in which they replace with the current source. Okay, now what I want to tell you is, what can be the maximum firing angle alpha? In this situation, what can be the maximum firing angle alpha? So you can also calculate the maximum firing angle alpha. So the maximum firing angle alpha can be pi. Just think about it. Okay, the maximum firing angle can be pi. Please think about it. But in case of current source, in this case, the maximum firing angle can be beyond pi. Okay, maximum firing angle can be beyond pi, or maybe let's see, is it beyond pi or maybe is it up to pi? Let's see. Let's try to think over it. Okay, so what I can do is, let's try to understand this. In this case, he is not saying that I naught is replaced for RL load. No, they have provided you I naught. It means the current is constant. In every situation, this current is constant. This current is constant. It means the average output voltage will be, what is the average output voltage? It will always be 2 Vm by pi cos alpha. It will always be 2 Vm by pi cos alpha. Okay, because the current source is replaced. There is a current source. It is not replaced for RL load. There is a difference. There is a difference between replacing the RL load with a current source and only current source is given. There is a difference in that. What is that difference? Let's try to understand that. Let's say there is only current source is given. It is not written that it is replaced for RL load. It is not written that it is replaced for RL load. It is given like this. Now we know that if current source is there, then current will always be continuous and current will always flow. So you can say that the conduction will always be continuous. First of all, this will always be continuous, irrespective of alpha. Whether you take alpha greater than theta z or less than theta z is not defined here. Okay, so you can say irrespective of alpha, the conduction is always continuous, and this will be my average output voltage. Always, this will be my average output voltage. Now the question is up to what alpha you can increase. What can be the maximum alpha you can increase? So alpha max is again pi. You can see that at alpha equal to 0, it is maximum positive, and alpha equal to pi, it is maximum negative. So you can increase alpha up to pi. This is the maximum alpha. Okay, from maximum positive to maximum negative you can take. Alpha max is pi. Okay, and up to pi, it will always be continuous, because there is no theta z point here. There is no theta z point here. If you want to calculate the wave shape, let me show you the wave shape. This is my supply voltage. This is my supply voltage, and let's say you are firing it at an angle alpha. This is my angle alpha. So at this instant T1, T2 are fired. At this instant T3, T4 are fired. At this instant again T1, T2 are fired. Okay. So now I want to plot V naught T. This is my VST, guys. This is my VST, and I want to plot V naught T. So V naught T will be equal to, since T1, T2 are conducting from this point, so V1, V2 will be same as the supply voltage. It will be same as the supply voltage, you can see that. And then after this, T3, T4 are fired. Whenever T3, T4 are conducting, output voltage is minus of VST. So just change the sign of this, so it will become opposite. So the output voltage will look like this. Output voltage will look like this. Is it clear, guys? Tell me. I hope it is clear. So this will be my output voltage in constant current source case. And what about the supply current? What about the supply current? You know that from this alpha to pi plus alpha, T1, T2 are conducting. T1, T2 are conducting. It means this constant current I naught will come like this. It will go like this and it will come like this. And then it will go like this. Is it fine? It means the supply current will also be positive. The supply current will also be positive. I naught will flow like this. Is it fine? So the supply current from alpha to pi plus alpha, the supply current will be positive and it will flow like this. Okay, this current is I naught. Now from pi plus alpha to 2 pi plus alpha, from pi plus alpha to 2 pi plus T3, T4 are conducting. It means this output current will flow in opposite way. Now this output current will flow in opposite way. So the current has to be negative. I hope it is clear to everyone. So this will be my supply current. This will be my supply current. Is it fine, guys? So I have plotted the supply current also. It will be a square wave. Supply current will always be a square wave, and alpha can be increased to pi. Now what is the difference in saying that it's a current source or RL load replaced with a current source? What is the difference in that? Whenever RL load is replaced with a current source, remember there is a concept of theta z. RL load can be replaced with current source if alpha is less than theta z. Then only you can replace RL load with a current source, and the current source value is this. But whenever only current source is given, there is no concept of theta z. Always the conduction will remain continuous and there is no concept of theta z. So please try to understand this point. Whenever you have RL load, there is a limitation of replacement of I naught. I mean, with this I naught, there is a condition of alpha, that alpha must be less than theta z. Then only you can replace RL load with a current source. If alpha is greater than theta z, it will be discontinuous and you can't replace RL load with current source. In discontinuous conduction, you cannot replace this RL load with constant current source. Only in continuous conduction you can replace it. So whenever you have RL load, this is the main difference. Along with the current source, if you are replacing RL load with the current source, you have to mention the theta z part, or you have to mention the alpha, and that alpha should be less than theta z. If alpha is greater than theta z, you cannot replace RL load with the current source. Conduction will become discontinuous. But in case of only current source, let's say this is given, so you don't know that this is replaced for this is the replacement for RL or not. It means what we do is we will always take it constant. If it is always constant, whatever alpha you take, conduction will always be continuous and the average output voltage will always be this. I hope it is clear to everyone. So please be careful when you are replacing RL with a current source and you are taking only current source. Okay, so there is a difference. Now let's come to RLE load. Now this RLE load is again very interesting. I have taught you about RL load. Using the RL load, I taught you about single R and single L load also. Now using RLE load, you can also understand everything. Like if you take E equal to 0, it will be RL again. If you take R equal to 0, it will become LE again. If you take L equal to 0, it will become RE again. Okay, so you can see that this is the universal situation. From this situation, you can understand every type of situation. I mean, every type of load you can understand. Okay, so let's try to understand this. First of all, what I want to do is, let's say you are firing at an angle alpha. At an angle alpha, you are firing T1, T2. And what I'm doing is, what I'm assuming that the conduction is just continuous. Let's first understand for just continuous, and then we will try for discontinuous and continuous. Okay. So for just continuous, let's try to understand. I fire at angle alpha. So if you fire at angle alpha, what will happen is from alpha to pi, and then pi plus alpha. At pi plus alpha, you fire T3, T4. This is pi and this is pi plus alpha. Okay. Please be careful, guys. This time, this is very difficult. So you have to understand. Okay. Now from alpha to pi plus alpha, T1, T2 will conduct, because I am taking just continuous case. Because here also there will be three cases: just continuous, continuous and discontinuous. So I am taking just continuous case first. So in just continuous case, the current will be like this. At this pi plus alpha, it will become 0. And then again it will start from here, pi plus alpha. And the output voltage will be like this. For just continuous case, output voltage will be like this. Output voltage will be like this. Is it fine, guys? This will be my output voltage. And you can see that the current is starting from 0 again. Okay. It starts from 0 again. So it's for just continuous. So in just continuous or continuous, in both the cases, for just continuous and continuous, in both the cases, output average voltage V0 average will be equal to 2 Vm by pi cos alpha. 2 Vm by pi cos alpha. Okay. Output average voltage will be 2 Vm by pi cos alpha. And what is output current? What is the output average current? We know that whatever the output average voltage is, VLT average will be 0. VLT average will be 0 because this current will be periodic, because R is there. Whenever R is there, remember, the current will always be periodic. It doesn't matter the conduction is continuous or discontinuous. It doesn't matter. Whenever R is there, current will be periodic. If current is periodic, then the average voltage across inductor will be 0. It means the total output average will be utilized in E and R. It means V0T average will be equal to, how to calculate this V0T average? I can write that V0T average can be utilized. V0T average is equal to E plus VRT average. You can write it like this. Okay. V0T average is equal to E plus VRT average. Now what is this VRT average? V0T average is equal to E plus R into I0T average. So from here you can calculate I0T average also. So I0T average will be equal to V0T average minus E divided by R. This way you can write I0T average. Okay. And V0T average is this value for continuous and just continuous conduction. I think it's easy. You can easily solve it for continuous and just continuous. But we have to check when the conduction will be continuous and when the conduction will be just continuous. We have to check. We have to calculate that alpha, beyond which the conduction will become discontinuous and below which the conduction is continuous. We have to understand that alpha. We have to calculate that alpha. How to calculate that? By writing the current equation. Okay. Now first, what I need to do is, I need to write the current equation. How to write the current equation, guys? We know that at alpha, I am firing T1, T2. So it's like again AC transient. So you can say that across RLE, this supply voltage is connected at alpha. You can see that. At omega t equal to alpha, T1, T2 are get fired. So you can say that the supply voltage is connected in parallel with this RLE load at omega t equal to alpha. So what I need to do is, I need to understand the AC transient situation. At omega t equal to alpha, I'm switching the supply voltage across RLE load. Okay, this is R, this is L, this is E. So across RLE load, I am switching on the supply at omega t equal to alpha. Now what is the supply current? Can you tell me what will be the current? This is Vm sin omega t. Calculate this current I naught t. So I naught t will be equal to, there are two sources. One is the supply voltage, one is the E. So we can use the superposition. I have told you in the previous class, the current will be Vm by Z. First of all, let's try to calculate the current due to the source voltage, AC source voltage. Vm by Z sine of omega t minus theta Z. I am deactivating E first. I am not looking at E. I am looking only on RL and this AC voltage. So due to the RL and the AC voltage, this is the steady state current minus Vm by Z sine of alpha minus theta Z e to the power minus R upon omega L, omega t minus alpha. This is the total current due to the AC source only. Okay, this is the total current due to the AC source only. Now the DC source. The DC source will provide the current in this direction. Okay, so minus E by R into 1 minus e to the power minus R by omega L, omega t minus alpha. Okay, this will be my, this will be the current due to this E. This will be the current due to this E. Is it fine? Now what we can do is, we got the current equation. Now we can calculate that boundary alpha, that alpha for which the conduction is just continuous. Now tell me how to calculate that alpha. How to calculate that alpha for which the conduction is just continuous. What you can do is, we know that at omega t equal to alpha the current is 0. But if the current is just continuous, at pi plus alpha it is again becoming 0. At omega t equal to alpha this is 0. You can check it. At omega t equal to alpha you can put omega t equal to alpha and you can see that this will become 0. You can see it yourself. But it should be 0 at omega t equal to pi plus alpha also, because the conduction is just continuous. If the conduction is just continuous, it means it should become 0 again at pi plus alpha. So please do that for just continuous conduction. For just continuous conduction, at omega t equal to pi plus alpha, it has to be 0. So what you do is, you put omega t equal to pi plus alpha in this expression and make it equal to 0. Okay, so it will be Vm by Z sine of pi plus alpha minus theta Z minus Vm by Z sine of alpha minus theta Z e to the power minus R pi divided by omega L minus E by R into 1 minus e to the power minus R pi by omega L. I hope it is clear, and make it equal to 0. Now from this relation we can calculate alpha. How to calculate alpha, guys? First of all, let's simplify this. This is pi plus some angle. So this is third quadrant. So it will become minus Vm by Z sine of alpha minus theta Z. And here also you have the same term. This term is this, and this term is also the same. So you can take the common, take this term common, and you can write 1 plus e to the power minus R pi by omega L. And take this e on this side, e upon R into 1 minus e to the power minus R pi by omega L. Now what we can do is, we can take this in the denominator and calculate the alpha. Now, how to calculate that alpha? So alpha will be equal to theta Z plus sine inverse of E by R into Z by Vm into e to the power minus R pi by omega L minus 1 divided by e to the power minus R pi by omega L plus 1. Now it might look difficult for you. Okay, it might look difficult for you to remember, because many students think that, sir, it is very difficult to remember. How to remember this? How to memorize this? If your practice is good, only 3 lines you have to write. You can calculate that alpha for which the conduction is just continuous, and this is not theta Z this time. It is actually less than theta Z. Why? Because this E is in opposite polarity. E is in opposite direction. That's why that alpha for which the conduction is just continuous is less than theta Z this time. In RL load, it was theta Z. You can see that if you put E equal to 0, If you put E equal to 0, then this load become RL load. If E is 0, then this term will be gone. This term will be gone and alpha equal to theta z. So from this condition, you can also calculate the previous condition. For RL load condition, you can calculate that. So if you put E equal to 0, then you can see that alpha equal to theta z. But if there is E, then alpha and this quantity will be negative. This quantity will be negative. Why it is negative? Tell me guys, why it is negative? E is positive, Z is positive, Vm is positive, R is positive. Look at this quantity. This will be less than 1. So this numerator will be negative. So this inside term is negative. That's why I'm saying that is the alpha will be less than theta z this time. Okay? Alpha will be less than theta z. It means you can calculate this alpha. Let's call it alpha JC. Let's call it alpha JC. Just continuous. So now I can comment that if alpha is less than alpha JC, if alpha is less than alpha JC, then the conduction is continuous. Conduction is continuous and V naught T average will be equal to 2 Vm by pi cos alpha. If alpha is equal to alpha JC, which I have already calculated, then the conduction is just continuous. Just continuous and V naught T average will be equal to again 2 Vm by pi cos alpha. Okay, and if alpha is greater than alpha JC, the conduction will become discontinuous. Conduction will become discontinuous. Conduction will become discontinuous and V naught T average will not be this. V naught T average will contain the beta term. We have to check. We have to check what will be this V naught T average. Okay. 2 Vm by pi cos alpha for continuous and just continuous conduction. But for discontinuous conduction, this average output voltage will not be the 2 Vm by pi cos alpha. It will be different. It will contain the beta, the extinction angle. Okay. Now we have to check what will be the V naught T for discontinuous conduction. Okay, let me tell you guys for discontinuous conduction. So we can draw again for discontinuous conduction. Let's see whether I have RLE load or not somewhere. Okay, I don't have the RLE load. So what we can do is we can plot it here only for discontinuous conduction. So I told you about the continuous and discontinuous, continuous and just continuous conduction. This will be the wave shape. Okay. Now I want to draw it for discontinuous conduction. So let's draw it for discontinuous. Let me remove this. Okay. Now let's come to the discontinuous conduction. Okay. Let's draw it for discontinuous conduction. If you want to draw it for discontinuous conduction, at alpha, the conduction will start and at alpha T1, T2 will start. But at pi plus alpha, T3, T4 will get fired. T3, T4 will get fired. Fine. So the current will start from alpha and it will become 0. It will become 0 before this pi plus alpha. Okay, before pi plus alpha. It is becoming 0 at this beta instant. We call this instant as beta. So it is becoming 0 at this beta instant. Now tell me, what will be the output voltage wave shape? So from alpha to beta, the output voltage wave shape will be same as the supply voltage. This is alpha, this is beta. Okay. Now from beta to pi plus alpha, current is 0, but it doesn't mean that the output voltage will also be 0. If there is no current in this load, then what will be the output voltage, guys? There is 0 drop here and there is 0 drop here. So this E will appear between these two terminals. Na? This E will appear between these two terminals because there is no voltage across R, there is no voltage across L. This E will appear between these 2 points. So you can say that from beta to pi plus alpha, E will be there. E volt will be there. Is it fine? E level will be there. And then at pi plus alpha, you have fired again T1, T2, T3, T4 you have fired. So the output voltage will be same as the supply voltage. Okay. This is 2 pi plus alpha. So again from this point, output voltage will start like this. output voltage will start like this, okay, and the current will again start from 0. It will go like this. Is it fine, guys? This will be the current, and this will not be up to, I mean the output voltage will not be up to again 2 pi plus alpha. The output voltage will be, it will become 0. You can see that the output voltage will look like this. At this instant it will stop because the current has stopped at this instant, okay. From this instant to again 2 pi plus alpha, it will remain as E, okay, and then it will start again, and then it will start again like this. I hope it is clear. So now if you want to calculate the average output voltage, how to calculate the average output voltage, guys? The average output voltage will be equal to, the period is pi, 1 over pi. The period is pi, 1 over pi, from alpha to beta. From alpha to beta, you have Vm sin omega t. Vm sin omega t d omega t. But from beta to pi plus alpha, it is E d omega t. The output voltage is E level, at E level. So you have to take average like this. Is it clear? So if you solve it, it will be Vm by pi. Integration of sign is minus cos, upper limit minus lower limit. It will be cos alpha minus cos beta plus E into pi plus alpha minus beta divided by pi. Okay, this will be my average output voltage now. Now you can see that we have to calculate beta, which is very difficult to calculate. Okay, so in discontinuous conduction, this will be my average output voltage. Okay, and in continuous conduction, this will be my average output voltage. And you can see that in discontinuous conduction, before the next cycle, the output voltage is E. Before the next cycle, the output voltage is E. You can see that the output voltage is E. Before the next cycle start, the output voltage will be E. Now, for discontinuous conduction, there is a minimum alpha. There is a minimum alpha that you can take, okay. What is that minimum alpha? Let me tell you, guys. Let me tell you what is the minimum alpha for discontinuous conduction. Let's say the conduction is discontinuous. If the conduction is discontinuous, it means this output voltage, before firing this T1 and T2, output voltage has the value as E. Output voltage is at E level. Output voltage is at E level. What does it mean? It means if you want to fire T1, T2, this supply voltage has to be greater than E. Then only you can fire it. Then only the current will start flowing. If this supply voltage is greater than E, then only the conduction will start. Is it fine? Then only the current will start. So you can say that Vm sin omega t has to greater than E, greater than equal to E. So from here, omega t has to be greater than sine inverse of E by Vm. This I call theta. So this alpha has to be greater than theta. Alpha has to be greater than theta for discontinuous conduction. Otherwise, the thyristor will not get fired, because you can see that. You can see that before T3, T4, output voltage is E. Before T1, T2, again at this instant, T1, T2 are get fired. So before T1, T2 are fired, this is the E level. So if this voltage is E, then this supply voltage has to be greater than E. Then only the current will start in this direction, and then only they will start conducting. So for discontinuous conduction, alpha minimum is this theta. For discontinuous conduction, alpha minimum is this theta. Okay? Alpha minimum is this. And what is alpha maximum? So this is my E level. So I told you this point is theta, this point is theta. So alpha should be greater than this theta so that you can fire T1, T2. This alpha has to be greater than this theta, and this alpha has to be less than this value. This is pi minus theta. Because after this point, you can also see that after this point, if you are firing, then it will not get fired. Why it will not get fired? Because the supply voltage is less than E. So alpha minimum is this theta, and alpha maximum is pi minus theta. If this point is theta, this will be pi minus theta. Okay. So for discontinuous conduction, For discontinuous conduction, I have calculated this V naught T average. V naught T average is this value, and alpha minimum is theta, and alpha maximum is pi minus theta. Pi minus theta. Okay, I have told you for discontinuous conduction. Now for continuous conduction or just continuous conduction, let's say you fired it. Let's say you fire at some angle alpha and the conduction is continuous. The conduction is continuous or just continuous. So you can see that at alpha JC the conduction is just continuous. Okay, alpha JC the conduction is just continuous, and we have calculated alpha JC from here. The conduction is just continuous for alpha JC. Now if you want to decrease the value of alpha, then conduction will become continuous. Let's say you start firing at alpha JC. At alpha JC the conduction is continuous, just continuous. Now you start decreasing the alpha. If you start decreasing the alpha, then alpha, you can decrease alpha up to 0. So in just continuous or continuous, alpha mean can be 0. In continuous conduction, or you can say for just continuous, alpha is fixed actually, but for continuous conduction alpha mean can be 0. Why it is 0? Why it is 0? Can you take alpha mean up to 0? Yes, you can take alpha mean equal to 0, but you have to start from alpha JC, or maybe some point which is greater than this theta. Okay, take alpha greater than this theta at the starting. Okay, at the starting you take alpha greater than this theta. You start from this. Let's say at this alpha conduction is continuous or just continuous. Now you start decreasing the value of alpha. If you keep on decreasing the value of alpha, it will remain continuous, and you can decrease up to 0. You can decrease up to 0. In continuous conduction, alpha mean can be 0. Okay, why? Because in continuous conduction this E will not appear at the output. If the current is always continuous, let's say, if current is always continuous, then this E will not be there at the output. E will never be there. E will be there if the current is 0. If the current becomes 0, then only E will appear at the output, and then only E will decide this firing angle, this minimum firing angle and the maximum firing angle. So you can see that in continuous conduction, E will never become up, E will never be there at the output. If you look at the output voltage wave shape, in continuous conduction, output voltage wave shape will be like this. Output voltage wave shape will be like this. In continuous conduction, this will be my output voltage wave shape. You can see that in the output voltage wave shape, there is no E. You can't see E. E will appear nowhere. So E will not decide the minimum alpha. Is it fine? That's why alpha minimum can be 0. Now what is alpha maximum? Alpha maximum will be equal to pi minus theta only. Okay? Alpha max can be pi minus theta. Why? Because let's say you keep on increasing alpha. Let's say you keep on increasing alpha. At this alpha the conduction was continuous. You keep on increasing alpha. So there will be some alpha JC at which the conduction will become just continuous. After that the conduction will become discontinuous. If it has become discontinuous beyond some point of alpha, if it has become discontinuous, then the maximum alpha has to be pi minus theta. Is it fine? So the maximum alpha has to be pi minus theta. Is it clear, guys? So remember this point. Remember this point. In continuous conduction, alpha min is 0, but alpha max is pi minus theta. You can't increase alpha beyond pi minus alpha in this situation, beyond pi minus theta. Okay, you can't take alpha beyond pi minus theta, because in continuous conduction, let's say you start from some alpha. You start at this alpha, the conduction is continuous, let's say. Now you start increasing alpha. If you start increasing the alpha, at some alpha JC, it will become discontinuous. Now if you further increase alpha, it will remain discontinuous. So I told you in discontinuous conduction, you cannot fire beyond this point. Okay, so this point is pi minus theta. So alpha max has to be pi minus theta here also. Okay, so be careful, guys. This is very important point. Okay, in RLE load, this is very important. Now the question is, we know that average output voltage is this. So this formula is applicable only up to alpha JC, only up to this angle alpha JC. This formula is applicable. Okay, and alpha JC is less than 90 degree. This theta Z is less than 90 degree and negative of this value. So this alpha JC will always be less than 90 degree. Since alpha is less than 90 degree, this average output voltage will always be positive. In continuous conduction, the average output voltage will always be positive. Average output voltage will never be negative. You can see that. In continuous conduction, average output voltage will be positive. But let's say somehow if we can make this alpha JC greater than 90, if alpha JC is made up of, let's say somehow we can make this alpha JC greater than 90. How to make it greater than 90? If somehow we can make this positive. If somehow we can make this positive, then this will be a positive angle. This is a positive angle. If you add them together, it might be possible that alpha JC came out to be greater than 90 degree. It means it is possible to make the continuous conduction beyond 90 degree also. Let's say this alpha JC came out to be greater than 90. It means up to this instant, let's say, up to this instant you can fire and it will remain continuous. This is my alpha JC. This is my alpha JC. It means you can fire up to this instant, you can increase alpha up to this instant and the conduction will remain continuous. This alpha JC is greater than 90. Let's say this alpha JC is 120 degree. Let's assume 120 degree. Now if you take alpha is equal to less than alpha JC, let's take it 100 degree. At alpha equal to 100 degree, conduction will remain continuous. Because alpha JC is 120 and alpha is less than alpha JC, so conduction will remain continuous and the average output voltage will be negative. Now in this case, average output voltage can be negative. It can be negative. You can make the average output voltage negative if alpha JC is greater than 120 degree. It means you can increase alpha up to 120 degree and the conduction will remain continuous and this formula will be valid. So in this formula, if alpha is greater than 90 degree, it will be negative. What does it mean? It means if somehow we can make this greater than 90, then we can increase alpha up to that level, up to that point, up to that alpha JC, which is greater than 90. Okay, we can increase up to that alpha and the conduction will remain continuous and the average voltage can also be negative. What does it mean? If the average voltage is negative, look at this point. This voltage is negative, this average value is negative, but the current can never be negative. Current can always flow in this direction. Now look, this voltage is negative and this current is positive. Now this will start delivering the power. This load will start delivering the power. It means we can revert the power flow. We can revert the power flow from the load end to the source end. We can revert the power flow. Okay, if alpha JC is made up, let's say if we somehow make this alpha JC greater than 90, okay, and if you take alpha equal to 100 or maybe 110 or maybe whatever, less than alpha JC but greater than 90. If you take alpha greater than 90 and less than alpha JC, then this average output voltage will be negative. If average output voltage is negative, if this average output voltage become negative, current will always be positive. This average output voltage will become negative, then you can see that the power can be delivered back. It will deliver back the power. It means it will deliver the power because the current is not coming into the positive sign. If the current is entering in the positive sign, it will absorb the power. But now the polarity has changed of the output voltage. Now it will start delivering the power. So you can invert the power flow. You can revert the power flow. Is it clear, guys? Now the question is how to increase this alpha beyond 90 degree. How to increase this alpha JC beyond 90 degree? There is only one way. We have to make it positive. We know that this quantity is negative. This is less than 1. This quantity is negative. To make it positive, what we can do is we can revert the polarity of E. We can revert the polarity of E. Is it fine, guys? If somehow you can invert the polarity of E, then it is possible to make this alpha JC greater than 90. To make this alpha JC greater than 90. And if alpha JC is greater than 90, you can increase alpha up to alpha JC for continuous conduction and you can see that the average output voltage may become negative and it may deliver the power. It may deliver the power back to the source. It means if you want to deliver the power back to the source, then what you do is you revert the polarity of E. Then only it is possible to make the power flow in the backward direction. Because in that case, if you revert the polarity of E, in that case, what you can do is you can increase alpha beyond 90 degree in continuous conduction. If this alpha is greater than 90 degree, this will be negative, and now the power flow can be reversed. Is it fine, guys? Have you understood it? So this is again very important point. I don't know how many of you have understood it, but this is again in RLE load, it is very important. So be careful about it. If you revert the polarity of E, then this alpha JC will be greater than 90. It means you can increase alpha to alpha JC. You can increase alpha up to alpha JC for continuous conduction. This formula is valid. And if alpha is greater than 90 degree, if you take alpha greater than 90 degree less than alpha JC, this formula is valid and it is negative. If it is negative, then the power can be delivered back to the source. Okay, so remember this point. It is again very interesting point, very important and very interesting point. Okay, so I told you about RLE load. Now let's come to the effect of the source inductance. In full wave rectifier, controlled rectifier, what is the effect of the source inductance? This is again a very important topic, guys. This is again a very important topic, so be careful. First of all, let's try to understand this without LS. If there is no LS, if LS is 0, then you can easily understand that. We have already done this before, na? Current source is there, first T1, T2 are conducting and then T3, T4 are conducting. So let me take LS equal to 0 first. If LS equal to 0, or what I can do is, wait a minute, what I can do is, I can duplicate it so that I can teach you in a better way. Okay, let's make it duplicate. Yes, now it is fine. Okay guys, now what I can do is, let's come to the effect of source inductance case. First you take LS equal to 0. What I have done is LS is 0. If LS is 0, there is no source inductance. Now we can plot for, okay, look at this. This is my alpha. At this instant T1, T2 start conducting. This point is alpha. At this instant T1, T2 start conducting. This is pi plus alpha. At this instant T3, T4 will start conducting. This is pi plus alpha. This point is pi. This point is pi. This is 2 pi. And this point is 2 pi plus alpha. Okay. This is 2 pi. And this point is 2 pi plus alpha. Okay, fine. Now, what is V naught T? At this instant, at alpha instant, we have fired T1, T2. We have fired T1, T2. If T1, T2 are fired at alpha, then the output voltage will look like this. It will go like this. This is my pi, okay? Output voltage will look like this. And then again at pi plus alpha, it will be like this. Is it fine, guys? Tell me. So this will be my output voltage. And the average value of the output voltage is 2 Vm by pi cos alpha. This will be my output voltage wave shape. Now, let's come to the source current. Whenever this T1, T2 are conducting, from this point to this point, T1, T2 are conducting up to pi plus alpha, up to this instant. At this instant, T3, T4 start conducting. At this instant, T3, T4 will start conducting. Okay, so you can see that from alpha to pi plus alpha, T1, T2 will keep conducting. If T1, T2 are conducting, then you can say that this current, the output current will flow like this. The output current will flow like this. Okay, so you can say that the source current will be same as I naught. So from alpha to pi plus alpha, the source current is same as the supply current. Okay, this is my I naught. The source current is same as the output current. Not the source. The supply current is equal to the current source value. Okay, it will flow like this and it will be positive. Now from pi plus alpha to 2 pi plus alpha. From pi plus alpha to 2 pi plus alpha, what will happen, guys? Tell me. From pi plus alpha to 2 pi plus alpha, what will happen? From pi plus alpha to 2 pi plus alpha, T3, T4 are conducting. So now this current I naught will flow like this. it will be opposite in the source. Is it fine, guys? I naught will be opposite in the source. So now this current will get reversed. Now this current will get reversed, and then again it will be positive. Okay, I hope it is clear to everyone. So this will be my source current. Source current will be a square wave. Okay, source current will be a square wave and it will flow like this if there is no LS, if there is no source inductance. But if you take the source inductance, let's say this time LS is non-zero, there is some source inductance, then what will happen? If there is some source inductance, then this source current cannot change abruptly. This source current cannot change abruptly because of the effect of the source inductance. The source current cannot change abruptly. This is the main problem, guys. Now, how to understand this? How to tackle this problem? To tackle this problem, we have to derive some formula and then we have to look at the effect of the source inductance. Okay? We have to derive some formula and we have to look at the effect of the source inductance. Now, what is that formula? Let's try to understand that. Okay, let's try to understand that. It's very simple. You don't need to remember anything. You don't need to remember any formula. It will take only 2 minutes because formula can disturb you. Formula can corrupt you. Okay. This is pi plus alpha. This is 2 pi. Okay. So now, here you have alpha, here you have pi, here you have pi plus alpha, here you have 2 pi. Okay, now look at this. The current and the voltage. So before alpha, before this alpha instant, T3, T4 were conducting. It means the entire current was flowing through this. I naught was going like this and it was coming like this. Okay. So before this alpha, the entire current was via T3, T4 and the source current was negative. And the supply current was negative because in this direction the current was there and I am taking this direction as positive direction. So the current was opposite. So I can take before alpha this source current or supply current will be negative minus I naught. And IT1 was 0. This current was 0. Okay, IT1 was 0. This is IT1. So IT1 was 0. Now at alpha what you have done is you have fired T1, T2. You have fired T1, T2. If you are firing T1, T2, what will happen? They will start conducting. But the problem is this source inductance will not make the current opposite abruptly. In the previous case, if you remember, in the previous case, as soon as you fire T1, T2, the current has reversed its direction. The supply current, the source current, AC source current. Previously it was in this direction, negative. Now abruptly it will change to this direction. Okay, but the problem is now we have the source inductance. Now the source inductance will not allow the current to change its direction abruptly. So what will happen is slowly this current will increase and this current will decrease. Slowly this T1 current and T2 current will increase. They will increase and they will decrease slowly. Okay, is it fine, guys? Slowly they will increase, their current will increase and their current will decrease. Now how to analyze this? Again, what you can do is you can take mesh currents. You can take mesh currents. You can assume that this current is I mu and this current is also I mu in this direction. Now you can see that this I mu is increasing. So this T2 current is increasing and T1 current is also increasing. But what about T3 current? In T3 current, in upward direction, the net current is I naught minus I mu. And in this thyristor, again upward current is I naught. Previously it was I naught. Now this I mu is opposing that. So you can see that as soon as this I mu is increasing, if this I mu is increasing, this thyristor current and this thyristor current will decrease. And this thyristor current and this thyristor current will increase. Okay, I hope it is clear to everyone. Now what we can do is, now we can analyze this and we can calculate the overlapping angle. Now you can see that all the thyristors are conducting now. During this overlapping interval, during this build-up process, during this I mu build-up process, You can see that this thyristor is conducting, this thyristor is conducting, this is conducting, and this is conducting. Since all the thyristors are conducting, this output voltage will be 0. Why it is 0? Because it is sorted, it is also sorted. So this point and this point will get sorted. That's why the output voltage will become 0. Output voltage will remain at 0. So there will be some overlapping interval. There will be some mu interval. And during that mu interval, output voltage will be 0. So from alpha to alpha plus mu, there is some minute interval. Output voltage will be 0. Okay. From alpha to alpha plus mu. Let's take that interval. This is alpha and this interval is mu. Okay. Let's call this point as alpha plus mu. Okay. This point is alpha plus mu. I hope it is clear to everyone. So during this overlapping interval, during this mu interval, what will happen is this thyristor current will increase from 0 to I naught. This thyristor current will increase from 0 to I naught. What about this source current? The source current in this direction was, previously it was minus I naught. Previously it was minus I naught, before alpha it was minus I naught. Now minus I naught will be there and 2 I mu. This I mu is on this direction and this I mu is also in this direction, plus 2 I mu. This is the source current IST now. And you can see that if I mu is changing from 0 to I naught, if I mu is changing from 0 to I naught, IS will change from minus I naught to plus I naught. It means this current will change from minus I naught to plus I naught. It will change from minus I naught to plus I naught. Is it fine? In this overlapping interval, this current IST will change from minus I naught to plus I naught. Fine? And this thyristor current will change from 0 to I naught. Is it clear, guys? Is it clear? I hope it is clear. Now, the problem is how to calculate this mu. And then after alpha plus mu, what will happen? Okay, I'll tell you how to calculate this mu. But before that, after alpha plus mu, what will happen? After alpha plus mu, this entire current is shifted in this direction. It will flow through T1, T2. It means this will be the T1 current up to pi plus alpha. Up to pi plus alpha. And this will be the source current up to pi plus alpha. Now at pi plus alpha, again there will be overlapping. Again there will be overlapping. If there is again overlapping, so there will be again. Now you can see that this T1 current has to decrease to 0 and the source current has to change from plus I naught to minus I naught. It has to change from plus I naught to minus I naught. Is it fine, guys? So this will be my source current. So there will be overlapping at alpha and at pi plus alpha and at 2 pi plus alpha. So at every firing instant, there will be overlapping. Now we need to calculate this overlapping angle mu. During this overlapping angle, the output voltage is 0. Okay. Now what will be the output voltage? From this alpha plus mu, the output voltage will be same as the supply voltage. Output voltage will be same as the supply voltage up to pi plus alpha. And then at pi plus alpha, there will be overlapping again. So output voltage will become 0 again. And then again, it will be minus of the supply voltage. I hope it is clear to everyone. This will be my output voltage. So there is a 0 gap. There is a 0 volt gap. Okay. There is a 0 volt gap in the output voltage. So if you want to calculate the average output voltage, if you want to calculate the average output voltage, it will be 1 over pi and the area has to be from alpha plus mu to pi plus alpha. Alpha plus mu to pi plus alpha, Vm sin omega t, d omega t. This will be my average output voltage. If you want to calculate it, it will come out to be V naught t average will be equal to Vm by pi. And the integration of sine is minus cos, upper limit minus lower limit. So it will be cos alpha plus cos of alpha plus mu. Okay. This will be my average output voltage. Now the question is, what is this mu? How to calculate this mu, this overlapping angle? How to calculate this overlapping angle? Tell me, guys. How to calculate this overlapping angle? To calculate this overlapping angle, what we are going to do? We are analyzing the overlapping interval. During the overlapping interval, all the 4 thyristors are conducting. So the circuit will look like this. All the 4 thyristors are conducting. So the circuit will look like this. During this overlapping interval, the circuit will look like this. This is the circuit which will work. And you have a current source I naught. Okay, this is the circuit which will work. And this is LS. Now there are 2 current. One is this current I mu and one is this current I mu. And there is one I naught current here. There was one I naught current. I mean, this I naught current was making loop like this. Okay. So there is one more I naught current was there. Okay. Now if you want to do the if you want to apply the KVL in this loop, if you want to apply the KVL in this loop, then this is Vm sin omega t. Vm sin omega t minus this drop. What is this drop? This drop is Ls into d by dt of net current in this direction, because you are going in this direction. So net current in this direction is I mu and I mu, 2 I mu minus I naught. So it will be 2 I mu minus I naught equal to 0. Okay, you can write the KVL like this. Now you can solve it. Vm sin omega t is equal to 2 Ls d I mu by dt. This way you can write this KVL and take this dt on this side. So d I mu is equal to Vm sin omega t divided by 2 Ls dt. Now you divide with omega and multiply with omega. So d I mu is equal to Vm sin omega t divided by 2 omega Ls d omega t. So you divide it with omega and multiply with omega. It will be like this. This will be d I mu. Now what you can do is you can integrate on both sides. You can integrate on both sides. Now this I mu is changing from 0 to I naught, and this is changing from alpha to alpha plus mu. Omega t is changing from alpha to alpha plus mu. Okay. Now you can calculate this. So I naught came out to be Vm by 2 omega Ls, Vm by 2 omega Ls into sine of omega t. The integration of sine of omega t is minus cos. Okay. Integration of sine is minus cos, upper limit minus lower limit. So it will become cos alpha minus cos of alpha plus mu. So from here you can calculate the mu angle also. From here you can calculate the mu angle and cos of alpha plus mu. You can take this cos of alpha plus mu, put it here, and you can calculate the average output voltage also. Okay, so the average output voltage will get reduced. It will not be 2 Vm by pi cos alpha like in this situation. It was 2 Vm by pi cos alpha. Now this average output voltage will get reduced. This is less than that. How much value is reduced? How to calculate that? What you can do is you can calculate cos alpha plus mu value from here. So it is cos alpha minus cos alpha plus mu will be equal to 2 omega Ls I naught upon Vm. We have calculated this value. So you can calculate this value, now cos of alpha plus mu. From this you can also calculate the mu value. Overlapping interval value you can also calculate. So cos alpha minus 2 omega Ls I naught by Vm. This is the expression I have for cos alpha plus mu. Now what you can do is you can put this cos alpha plus mu value in this expression. So the average output voltage will be Vm by pi into cos alpha plus this value. What is this value? This value is cos alpha minus this. So you can put it like this, cos alpha minus 2 omega Ls I naught by Vm. Okay, you can calculate like, you can put it like this. So what you can do is you can take it, you can write it like this, 2 Vm by pi cos alpha minus 2 omega Ls I naught by pi. You can see that. So previously it was 2 Vm by pi cos alpha. Now it is decreased by this factor. So you can see that due to the source inductance, due to the effect of the source inductance, due to this source inductance, this average output voltage will get reduced. Previously it was 2 Vm by pi cos alpha, now it is 2 Vm by pi cos alpha minus this value. I hope it is clear to everyone. I hope it is clear to everyone. Okay, so I told you what will be the average output voltage due to the source inductance. Now this topic is over. Okay, I have covered all the topics in phase control rectifier, guys, at least the single phase control rectifier. Okay, the single phase control rectifier is over. Now it's time for the semi converter. It's time for the semi converter. Let's look at the semi converter also. Let's look at the semi converter also. So in semi converter, what is the new thing? Tell me, guys, what is the new thing in semi converter? So in semi converter, there are two diodes. There are two types of semi converter. One is this, okay, and there is one more semi converter in which two diodes are connected like this. Connected like this. This is again a semi converter. Two thyristors on this side and two diodes on this side. Now in semi converter, what we have is there is an inbuilt freewheeling action. There is an inbuilt freewheeling action in semi converter. And what is that freewheeling converter? Now, what is that freewheeling action? Let me tell you. Let's say this is my alpha. Let's try to understand the wave shape. This is pi plus alpha. This is pi. This is 2 pi. And we have 2 pi plus alpha. Okay. Now if you look at this carefully, then I can say that this is pi plus alpha. You have 2 pi here. Okay. And this is 2 pi plus alpha. Now we can see that let's replace it with a current source because it will be easier to understand then. Okay, let's replace it with a current source. Let's say the load is a current source. Let's replace it with a current source. Let's not take RL load. Let's replace it with a current source I naught, because I don't want to take RL load. I want to understand it with current source. So let's replace it with a current source. Now you can see that, let's assume that this is 0 and this is VST. Let's assume that this is 0, this is VST. Now tell me, in which configuration these two diodes are connected? Is it common anode or common cathode? Tell me, guys, in which configuration these two diodes are connected? Are they connected in common cathode or common anode? Tell me, are they connected in common anode or common cathode? Now you can see that their cathode is common. You can see that their cathode is common. Their anode. This is called anode. No? So their anode is common. So they have common anode configuration. Their anode is common. This point is anode. So their anode is common. Whenever two diodes are under common anode configuration, the diode which has the lowest voltage on cathode will conduct. Okay. The diode which has the lowest voltage on its cathode will conduct. Okay. Now tell me, in the first half cycle, if you look at this, in the first half cycle, this VST is positive and this is 0. So tell me which one is the lowest voltage? D1. So you can see that before alpha, out of these two diodes, D1 was conducting. This current was coming through D1. And the thyristor T1 is not get fired, because thyristor T1 will get fired at alpha. Now tell me, what will be the path of this I naught? Obviously this cannot flow through this T1. So this current has to flow through T2. Okay, this T2 was conducting before alpha, T2 was conducting. Na? So you can say that this I naught will flow through D1 and T2. So there is a freewheeling action. It is sorted, it is also sorted. So the output voltage will remain 0. Before alpha, the output voltage will remain 0 and there will be no source current. Current is not flowing through the source. Current is freewheeling here. So I told you there is a inbuilt freewheeling action. So this is my inbuilt freewheeling action. Is it fine? You don't need to connect a freewheeling diode. Okay. So there is a freewheeling action here. So the output voltage will be 0 and output current is constant. Output current remains constant always. The source current is 0. The source current is 0. You don't need to plot this. This will always remain constant. because there is a current source, no? So it will always remain constant. Now the source current will be 0 because there is no current which is flowing through the source. This side current is 0. Entire current is flowing like this. Is it fine? So you can see that the source current is 0. Output voltage is 0. Before alpha, there is a freewheeling action, so output voltage is 0. Now at alpha, what we did is, at alpha, you have fired T1. If you have fired T1, T2 will get reverse biased because this voltage will appear here. This VST will appear here and that voltage will reverse bias this thyristor T2. As soon as this thyristor become reverse biased, it will turn off and the current will flow through D1 and T1. Is it fine? Now the current will flow through D1 and T1. D1, T1. Now the current will flow through D1, T1 and output voltage will be same as the supply voltage. This becomes 0 and this becomes VST. So the output voltage will be same as the supply voltage. So output voltage will be same as the supply voltage up to pi. And the supply current will be positive. Supply current from alpha to pi, the supply current is positive. Is it fine? Now what will happen after pi? After pi, let me tell you guys, T1 is conducting. Before pi, T1 is conducting. Now what will happen after pi? After pi, you can see that the voltage become negative. Supply voltage become negative. This T1 was conducting before pi. Now just after pi, the supply voltage is becoming negative. Supply voltage will become negative. It means this is negative and this is 0. Now tell me which diode will conduct. Because for diodes, you don't require any firing, no? You don't require any firing. So tell me after pi, this is negative, this is 0. Which one is the lowest voltage? D2 voltage is lowest. Okay, so now D2 will start conducting. Now D2 will start conducting and in the upper two devices, T1 is already conducting. So now T1, D2 will conduct. So there is again freewheeling action. There is again a freewheeling action and there is no source current. So you can see that from pi to pi plus alpha, from pi to pi plus alpha, the current, the source current will become 0. Okay, the source current will be 0. From pi to pi plus alpha, the source current will be 0. Okay, and the output voltage will also be 0. Output voltage will also be 0 because there is a freewheeling action. Now what will happen, guys? Now at pi plus alpha, you have fired T2. As soon as you fire T2, T1 will get turned off and the entire current will flow through T2, D2. Now T2, D2 will conduct. Now T2, D2 will conduct and the output voltage will be minus of the supply voltage. Output voltage will be negative of the supply voltage. So whatever the supply voltage is, negative of that is this. Okay, so the output voltage will be negative of the supply voltage. I hope it is clear. And the source current will be negative from pi plus alpha to this 2 pi. From pi plus alpha to 2 pi, it was positive before, now it is negative, minus I naught. So from pi plus alpha to 2 pi, it is negative, minus I naught. Now again from 2 pi to 2 pi plus alpha, from 2 pi to 2 pi plus alpha, you can see that again there is a freewheeling action. Who will conduct? T2 was conducting and we know that after 2 pi it becomes positive. This supply voltage is positive now. So now D1 will start conducting because this is positive after 2 pi. If it is positive, D2 will turn off, D1 will start conducting and in the upper devices, T2 is already conducting. So now you can see that during this small interval, T2 and D1 will conduct and there is a freewheeling action. So the supply current will again be 0 and the output voltage will also be 0. So now you can see that the output voltage will be there. There is a freewheeling action which is inbuilt in this circuit. If there is a freewheeling, whenever you have freewheeling diode, output voltage will never go to negative. Output voltage will never go negative. So this will be my output voltage. This will be my output voltage. It will never go negative. Now you can see that the average value of the output voltage, V naught T average will be equal to, you can take 1 upon pi and take the area alpha to pi, Vm sin omega t d omega t. Okay, and you can calculate this value. Vm by pi And the integration of sign is minus cos upper limit minus lower limit 1 plus cos alpha. Okay, this is my V naught T average. This is my V naught T average. I hope it is clear. Okay, and it will never be negative. It will always be positive. Wherever you have freewheeling diode, it will never be negative. It will always be positive. This will be my supply current. Now the supply current is discontinuous. You can see that. Supply current is discontinuous. I hope it is clear to everyone. Let's proceed, guys. Let's proceed with the second case. Now I have connected a freewheeling diode here. I mean, it's not required. It's not required in this circuit. There is an inbuilt freewheeling action. Why you require this freewheeling diode? Okay, though you have connected it, I understand that, but there is no requirement for that. Okay, anyway, let's come to the next thing. Now we have two diodes connected like this. Again, you replace it with a current source. Okay, let's take it as a current source. Replace this load with a current source. This is a constant I naught. Okay, you replace with a constant current source and try to calculate this. Try to calculate the output voltage, average output voltage. Okay, try to calculate that. First you have to draw the wave shape. Inbuilt freewheeling action is there already. Yes, in this device is in this case there is a freewheeling action. It's again a semi-converter. Okay, it's again a semi-converter. So there is again a freewheeling action. Let me tell you how. Let me tell you how. Again you can draw. This is my alpha. This is alpha. This is pi. This is pi plus alpha. This is 2 pi. And this is 2 pi plus alpha. Okay. Now at alpha, we have fired T1. But before alpha, T2 was not conducting. T1 is also not conducting. Because look at these two diodes. No? Let's say this is 0 volt. And this is my VST. Let's say before alpha, no one was conducting. The current was freewheeling through D1, D2. So the output voltage is 0. D1, D2 were conducting. D1, D2 were conducting. Okay, output voltage was 0. And output current will always remain constant because I have replaced with a current source. And IST. Here you have to write IST. The source current. The source current will also be 0. Okay, there was no source current. Before alpha, there was no source current. Is it fine? The source current was also 0. There was no source current. Now, at alpha, what you did is, at alpha, you have fired T1, T2. You have fired T1. You have fired T1 only. Since you have fired T1, what will happen, guys? Since you have fired T1, the current will flow through D1, T1. Because this will get reverse biased. Because as soon as you fire it, this VST will appear here. And VST is positive. This point is 0, this point is positive. So it will be reverse biased. So now D2 will not conduct. Since D2 is not conducting, so the current will flow through D1 and T1. Current will flow through D1 and T1. So the output voltage will be same as the supply voltage. Output voltage will be same as the supply voltage. From alpha to pi, this will be the wave shape of the output voltage. Fine? This will be my output voltage wave shape from alpha to pi. And the source current, the supply current will be like this. Up to pi. Now what will happen after pi? After pi, this is already conducting. But this become negative. This become negative. Okay? If it become negative, then what will happen, guys? If it is conducting, let's say that T1 is still conducting, then this voltage will become negative. If it is negative and if it is 0, then this D2 has to forward bias. It means now D2 will be forward biased. Is it fine? So just after pi, what will happen, guys? D2 will forward bias and this voltage will become 0. Here you have 0, here you have the negative voltage. So this will become reverse biased. Is it fine? Is it fine? So now you can see that D2 is conducting and D1 was already conducting. So now you can see that D1, D2 will keep conducting. Okay. Now D1, D2 will again conduct. So output voltage will remain 0. Source current will also remain 0. Now at pi plus alpha, what will happen, guys? At pi plus alpha, what will happen? You have fired T2. At pi plus alpha, you have fired T2. So as soon as you fire T2, what will happen? The output voltage will be minus of supply voltage, and now T2, D2 will conduct. The current will flow like this. T2, D2 will conduct. Okay. So the shape will remain same as was the previous case. The shape will remain same. Okay. Everything will remain same. Nothing new. Only thing is we have changed the configuration. Okay. Everything will remain same. I hope it is clear. So there is an inbuilt freewheeling action via D1, D2. Okay. Now we can see that during this interval D1, D2, during this interval also during D1, D2, and during this. So there is a freewheeling action via D1, D2. I hope it is clear, and the average value will remain same as the previous one. Okay. Everything remains same. So I hope it is clear. Now let's move to the three-phase circuits. So tell me, guys, are you getting all these points? Tell me, everyone, are you getting all these points? Can I proceed? Let's cover this three-phase control rectifier also, no? Or you want me to cover the DC-DC converter? Tell me. You want me to cover DC-DC converter or the three-phase converter? Tell me, everyone. I think we should continue with this part only. Tell me if you want me to DC-DC. If you want me to cover the DC-DC part, I'll do that. No problem at all. Okay. Let's continue with this because it's not that much. That much difficult. So we'll cover it, and the DC-DC part is also simple. It's not that much difficult. If let's say we are not able to cover the entire topic now, so we will take one dedicated session for that. Okay, in that session we'll cover that. Okay, so yes, three-phase. Yes, I'll come to three-phase converter. Now this is half wave controlled, and after that we'll come to the full wave controlled. Okay, so we'll understand everyone. Let's first try to understand this half controlled rectifier with R load. So I have taken this R load, and this is half controlled rectifier. So in this half controlled rectifier, in which configuration these thyristors are connected? Tell me, guys. In which configuration these thyristors are connected? These thyristors are connected under common. You can see that their cathode is common. So they are connected under common cathode. So the thyristor which has the highest voltage on its anode will be under forward blocking mode. That will be under forward blocking mode. The thyristor which has the highest voltage at their anode, the thyristor which has the highest voltage at their anode will be under forward blocking mode. And there is one more point. Let's say whether T1 is conducting or T2 or T3, whatever, the output voltage will be the phase voltage. It may be VAN or VBN or VCN. Let's say if T1 is conducting, then the output voltage will be VAN. If T2 is conducting, the output voltage will be VBN. If T3 is conducting, the output voltage will be VCN. Is it fine? So it means the output, at output you will have the phase voltages. So what we are going to do is, first let's plot phase voltages. So let's plot phase voltages. How to plot the phase voltage? The phase voltage plot is very simple. What you need to do is, first you need to draw the triangles. First you need to draw the triangular shape. So draw the triangular shape like this. Fine. This is my triangular shape. You draw the triangular shape like this, and then connect these caps. Connect these caps like this. Okay. These are my phase voltages. Now you can see that, and this is the origin line. This is the origin line. Now you can see that this is VAN, this is VBN, and this is VCN. Okay. This way you can draw the phase voltages. It's easy peasy. And remember, every triangle is of 60 degree. Every triangle is of 60 degree. Remember this point. Every triangle is of 60 degree. Every triangle is of 60 degree. Now what I need to do is I need to look at the output voltage. I need to look at the output voltage. What is output voltage? I need to look at this for some firing angle alpha, let's say. Now the firing angle is measured from this instant, because from this instant onward this thyristor will be under forward blocking mode, because VAN is the highest voltage. It means VAN will be, this thyristor will be under forward blocking mode. From this instant onward, the thyristor T2 will be under forward blocking mode. So the firing angle alpha 0 means this instant. This instant is represent alpha equal to 0 point. Alpha equal to 0 point. Alpha equal to 0 point for C. For C, this is alpha equal to 0. For B, this is alpha equal to 0. For A, this is alpha equal to 0. Why? Why I am taking this point as alpha equal to 0? Because the problem is, I told you, whenever it is under forward blocking mode, then only it get fired. And it will be under forward blocking mode after this instant. That's why we measure alpha equal to 0 for this thyristor at this instant. Okay. Now let's take alpha is some 30 degree. Now if alpha is 30 degree, alpha is measured from this instant. Remember, alpha is measured from this instant. Okay. Now if alpha is 30 degree, tell me the wave shape. From this instant, at this point, T1 get fired. At this point, T1 get fired. For alpha equal to 30 degree, I am plotting. At this instant, T1 will get fired, and at this instant, because for thyristor T2, T2 is connected to phase B. For thyristor T2, this is the starting point. From this point, 30 degree ahead. So at this point, T2 will get fired. Okay, at this point, T2 will get fired. Is it fine, guys? Similarly, for thyristor T3, this is alpha equal to 0 point, and 30 degree beyond that is this point, because I told you every triangle is of 60 degree. So the half of that triangle is 30 degree. Is it clear? So you can say that for T3, this is my starting point. At this instant, T3 will get fired. At this instant, T2 will get fired. At this instant, T1 will get fired. Is it clear, guys? Is it clear? Now I need to draw the output voltage. So the output voltage will be like this. From this instant to this instant, VAN will be there. It means phase A will conduct. Phase A will be at the output voltage. I hope it is clear. Now from this instant to this instant, phase B will be there. Tell me, guys, is it clear? Phase B will be there, and then from this instant to this instant, phase C will be there. So you can see that the output voltage, I have shown the output voltage in the blue color. Okay. So you can see the shape of the output voltage. I hope it is clear. I hope it is clear. Okay. So this is VAN, this is VBN, this is VCN. For every 120 degree, you can see that every thyristor conduct for 120 degree. And since the voltage is like this and the load is resistive, the current will also, current wave will also be the same. The current wave will also be the same. If you want to plot the current wave, the current wave shape will also be the same. Only thing is it is divided by R. So this is my current wave shape. You can see I have plotted with a different color. It's bit magnitude is bit lower. Why? Because we have divided it with R, but the wave shape will remain same. I hope it is clear. Okay. So the wave shape of the current will remain same. So I told you what is the output voltage wave shape, the blue color wave shape, and the current wave shape, the green color wave you can see. Now you can see that up to 30 degree, the current is just continuous. In case of resistive load, you can see that the current is just continuous. At this point, the current becomes 0. At the same point, it started upward. Okay. So you can see that the current is just continuous. So for alpha less than 30 degree in R load, conduction is continuous. Conduction is continuous. At alpha equal to 30 degree, conduction is just continuous. Just continuous. Alpha greater than 30 degree, conduction is discontinuous. We'll see that. Conduction will be discontinuous. Okay. Now what I need to do is I need to calculate the average output voltage. So the average output voltage is, what is the period of this wave? The period is 120 degree. 120 degree means 2 pi by 3. So period is 2 pi by 3. So 1 upon 2 pi by 3. 1 upon 2 pi by 3 integration. I need to calculate this area. What is this area? This length is alpha and this length, this point is pi by 6. So I am integrating it from pi by 6 plus alpha to, what is this point? You just add 120 to it. So it will be 5 pi by 6 plus alpha. If you add 120 to it, this point is pi by 6 plus alpha, you just add 120 to it. 120 means 2 pi by 3. You just add 2 pi by 3 to it and it will become 5 pi by 6 plus alpha. Okay. So we are integrating from pi by 6 plus alpha to 5 pi by 6 plus alpha. And voltage is VAN. VAN is Vm sin omega t. Vm sin omega t d omega t. Okay. Now you can calculate this value. This value came out to be 3 Vm by 2 pi, and the integration of sine is minus cos, upper limit minus lower limit. So it will be cos alpha. Do it yourself. Okay. 3 Vm by 2 pi cos alpha. Okay. This will be my average output voltage. This will be my average output voltage. Divided by R will be the average output current. But let me tell you guys, this is true for continuous conduction only. Up to this 30 degree, it is true. But if you take alpha beyond 30 degree, let's say you take alpha equal to 60 degree, then this average voltage will not be correct. The conduction will become discontinuous. Let's take it. Let's take alpha equal to 60 degree. So I want to take alpha equal to 60 degree. I want to plot alpha equal to 60 degree case. Okay. So first of all, let's plot the phase voltages. So the phase voltage will look like this. The phase voltage will look like this. Okay. Here you have omega t. This is VAN, this is VBN, and this is VCN. This is my phase voltages. Okay. These are the phase voltages. Now alpha is 60 degree. So obviously thyristor T1, for thyristor T1 it should start from here, but 60 degree beyond that, 60 degree beyond that is this point. At this instant thyristor T1 will get fired. Now what about T2? T2 will get fired at this instant. Okay. At this instant T2 will get fired. This is for thyristor T2. At this instant T3 will get fired. T3 will get fired at this instant. Okay. So I told you at this instant T1 will get fired, at this instant T2, and at this instant T3 will get fired. Now what I need to do is I need to plot the output voltage. So from T1 onwards, at this instant T1 it will get fired now. So the output voltage will be VAN. So VAN is this voltage. Output voltage remain at VAN up to this point. It will not go negative. Why? Output voltage can never be negative, because if output voltage is negative, then the current has to be negative. And negative current cannot flow. Negative current cannot flow via these thyristors. That's why after this point it has to be 0. Okay. You can see that the output voltage will look like this, and then it will be 0, and then VBN will start, and then VBN will start, and it will be like this, and then it will be 0. Okay. So you can see that the output voltage has the 0 gap. So the current wave shape will also be like this. The current wave shape will also be like this. Similarly, you can plot the previous part. Okay. So this will be my output voltage, the blue color. In the blue color, you can see the output voltage. Now, what will be the current wave shape? Since the load is resistive, so you can see that the current will also be like this, like the same. The wave shape of the current will also be like the same. divide by R. Whatever the voltage is, divide by R will be the current waveshape. So this way you can plot the current waveshape. There is no problem at all. Okay. Now, what is the average voltage? What is the average voltage in this case? V naught T average. How to calculate that average? That average is 1 upon 2 pi by 3. 1 upon 2 pi by 3, which is the period of this wave, 1 upon 2 pi by 3. And if you want to calculate the area under one period, what is this instant? Tell me guys. This length is alpha. And this point is pi by 6. So we have to integrate it from pi by 6 plus alpha to the upper point. This point is pi, up to pi. From this point, pi by 6 plus alpha to pi, we have to take the area. And the area of Vm sin omega t. D omega t. Okay. This will be the average output voltage. So it will be 3 Vm by 2 pi. And the integration of sine is minus cos upper limit minus lower limit. This will be the formula for average output voltage. If you take alpha greater than 30 degree, this formula is valid. Okay. If you take alpha less than 30 degree, this formula is correct because this is for continuous conduction. So remember this point. Whenever you have continuous conduction, this is the formula in 3-phase half controlled rectifier. Okay. And whenever you have discontinuous conduction, this formula is valid. Now, to what angle you can increase alpha? Obviously, you can fire up to this instant. Na? You can fire up to this instant. And what is this length? This length is 150 degree. So alpha max is 150 degree because alpha is measured from this. And you can fire T1 up to this instant. Beyond that point, you cannot fire T1. So you can see that that my alpha max is 150 degree. Okay. So alpha max, remember alpha max came out to be 150 degree. Alpha max is 150 degree. Okay. So I told you about the output voltage waveshape and the average output voltage for R load. And remember, if alpha is less than 30 degree, this formula is valid because the conduction is continuous. If alpha is greater than 30 degree, this formula is valid because the conduction is discontinuous. Now let's come to the next thing, RL load. So again in RL load, there are the possibility of continuous conduction and discontinuous conduction. So we are interested in just continuous case. Let's look at the just continuous case. At what alpha the conduction will become just continuous, and after what alpha the conduction become discontinuous, and for what value of alpha the conduction is discontinuous. So we are interested in that part only. So let's try to understand that. This point is N. We call it VAN, this is VBN, and this is VCN. And the load is RL this time. So what we are going to do is, again, plot the phase voltage. Plot the phase voltage. These are the triangles first you have to show in the phase voltages. Okay, and then this is VAN, this is VBN, and this is VCN. Okay. Now, let's say you are firing at some angle alpha, and at that angle alpha, the conduction is just continuous. Okay. Let's call that an angle. Let's show that at an angle alpha, that alpha is shown here. Alpha is measured from this point. Let's say you are firing at this instant, or maybe some other instant. Let's not take this. Let's say that this is the instant, or maybe this is the instant at which you are firing T1. So T1 will get fired at this instant, T2 will get fired at this instant then. Okay, T2 will get fired at this instant. So this is my T2 instant, and this is the T3 instant. Okay, this is the T3 instant. So now the current is just continuous. The current is just continuous. It means output voltage will start from here, and the current, let me show the current also. So current can be shown with the, I think with the white color. So from here the current will start like this and it will be some positive value at this point. Current will have the positive value at this instant, okay? So now the current has the positive value. So what I need to do is, the current has become the positive value at this instant. If the current is positive, this thyristor will not turn off. Why? Because we know that T2 will not get fired. T2 will get fired at this instant. T3 will get fired at this instant. So there is no other way for the current flow. So current has to flow because the inductor will not stop the current. Current has developed some value in inductor. So this T1 has to conduct. If T1 has to conduct, the output voltage will remain as VAN. So it will go negative. So the output voltage will go negative and the current will become 0 at this instant. Okay? Because I am writing for just continuous case. Na? So current is becoming 0 at this instant. Is it fine? So you can say that the output voltage will be negative and it will be negative up to this instant. Is it fine? Up to this instant it will remain negative and then again it will become positive. I hope it is clear. I hope it is clear and then again it will become positive. So this will be the wave shape of the output voltage and the wave shape of the current. Current is just continuous. Current is just continuous. This will be the wave shape of the current. I hope it is clear. Now how to calculate this current equation and what is this alpha? We need to calculate this alpha. What is this alpha? How to calculate that? For that I need to write the current equation. And how to write the current equation? We know that Vn is the output voltage. At this instant Vn is the output voltage. So what you are doing is you are connecting, you have RL load and you have the switch. Switch means this thyristor T1. Now you are connecting this switch on, you are turning this on at this instant and this instant is pi by 6 plus alpha. You can see that this is pi by 6, this is alpha. So you are turning this switch on at pi by 6 plus alpha. Okay? And I need to write the current equation. What is the current? So the current equation is, it has steady state part and the transient part. Okay? So the steady state part is Vm by Z sine of omega t minus theta z. Now what is the transient part? At this instant this current has to be 0. But this is not 0. You can see the value. If you put pi by 6 plus alpha, it will become Vm by Z sine of pi by 6 plus alpha minus theta z. It is not 0. To make it 0, I have to subtract the same value. Vm by Z sine of pi by 6 plus alpha minus theta z e to the power minus r by omega L. Here you have to put omega t minus pi by 6 plus alpha. Okay? This should be the power. Is it fine, guys? So we have plotted this current. This is my IT. This is my IT. This is the current equation. Okay? This is the current equation. Fine? So I told you that this is the current equation. If this is the current equation, then it is starting at this point. At this point it is 0. It will again be 0 at this point. And what is this length? This length is 120. After 120 degree, it will be 0. Now we know that this instant is, what is this instant? This instant is pi by 6 plus alpha. If you add 120 to it, it will become 5 pi by 6 plus alpha. Okay? So at 5 pi by 6 plus alpha, again it should be 0. So what you do is, you put omega t equal to 5 pi by 6 plus alpha. Okay? And make this current equal to 0 again. And you can calculate the alpha value. That alpha will be just continuous conduction. That alpha will be for just continuous conduction. You can calculate that alpha. I am not interested in that alpha. I told you the method, how to calculate the alpha for which the conduction is just continuous and for which the conduction is, beyond which the conduction will become discontinuous. If you increase this alpha, from here you calculate alpha JC now. So if alpha is greater than alpha JC, it will be discontinuous conduction. And then you have to calculate that beta angle, extinction angle. An extinction angle you can't find. Okay? So the conduction will become discontinuous. If alpha equal to alpha JC, conduction is just continuous. just continuous, if alpha is less than alpha JC, conduction is continuous. Conduction is continuous. Okay. And for these two cases, the average output voltage will be V naught T average will be equal to 3 Vm by 2 pi cos of alpha. I think I have written it wrong. This is 3 root 3 Vm. Please correct it. The average output voltage in continuous conduction should be 3 root 3 Vm by 2 pi. Please correct it. It should be 3 root 3 Vm by 2 pi cos alpha. Okay. So here also it should be 3 root 3 Vm by 2 pi cos alpha. This will be my average output voltage because the conduction is continuous. That's why this will be my average output voltage in just continuous and continuous. So we are interested only in these two cases. Okay. We are interested in only in these two cases, in continuous and just continuous. Discontinuous conduction is not required for us. Why? Because for discontinuous conduction you need beta, and beta is not solvable. You can't solve beta. That's the main problem. Okay. So I told you how to calculate for continuous and discontinuous conduction what is the average output voltage. Once you get this average output voltage, now we know that average output voltage will be equal to R into I naught T average. Because VLT average is 0. Why VLT average is 0? Why this average voltage is 0? Because the current is periodic. Whether the conduction is continuous or discontinuous, current will always be periodic because R is there. Na? So current will be periodic. If current is periodic, you can see that this average voltage, VLT average will be 0. Okay, VLT average will be 0. So V naught T average, whatever the output average is, that will be equal to R into I naught T average. From here, you can calculate I naught T average. I naught T average will be equal to V naught T average upon R. V naught T average upon R. Is it clear, guys? So this way you can calculate the I naught T average. I hope it is clear. Okay, I hope it is clear. So I told you how to calculate the current average value and how to check for continuous and discontinuous conduction. Now let's proceed. Let's proceed with the next case. You have only L. In case you have only L, then in the same case you can use the L case also. Na? You put R equal to 0. Whatever this alpha JC came, in that alpha JC you put R equal to 0. Na? So if you put R equal to 0, you will get the case of pure L. So you do it yourself. Okay. So calculate this alpha JC and then put R equal to 0. If you put R equal to 0, theta Z will be 0. This theta Z will be 0 and calculate alpha JC. This theta Z will be, okay, this theta Z will be 90. Please excuse me. So if R is 0, then theta Z will become 90. So you can put theta Z as 90 and calculate alpha JC. Okay. Now calculate alpha JC. Let me tell you guys, you have to calculate alpha JC. If alpha is less than alpha JC again, now this alpha JC will be different. Because here in this case, theta Z is 90 degree. So the relation will remain same, na? This relation will remain same, only theta Z will become 90 degree. Okay. If theta Z is 90 degree, put theta Z equal to 90 degree and calculate alpha JC. Once you get this alpha JC, then you can comment that if alpha is less than alpha JC, continuous conduction is there. Continuous conduction is there. And if alpha is equal to alpha JC, just continuous. Just continuous. And if alpha is greater than alpha JC, discontinuous. Discontinuous. Now let me tell you guys, for continuous conduction it is 3 root 3 Vm by 2 pi cos alpha. Okay. This will be my average output voltage. Now if alpha is less than 90 degree, if alpha is less than 90 degree, if alpha is less than 90 degree, this will be positive. At alpha equal to 90 degree, this is 0. V naught T average is 0. V naught T average. And we know that in just continuous case, average output voltage is 0 because it's a pure inductor. In pure inductor, in just continuous or discontinuous conduction, current will be periodic. Current will be periodic, and if the current is periodic, then the average output voltage will be 0. So you can see that alpha equal to 90 degree, the average output voltage is 0. It means alpha JC has to be 90 degree here. Alpha JC has to be 90 degree. Okay. From here you can comment on alpha JC also. Because if alpha is less than 90 degree, it is positive. So the average output voltage across inductor is positive. It means the current will be continuous, aperiodic and rising. Aperiodic and rising. Why it is rising? Why it is rising, guys? Because average voltage is positive. Because this average voltage is positive. That's why the current is rising. If average voltage is 0 at alpha equal to 90 degree, the average will become first times 0. We call it just continuous. So for just continuous conduction, current is periodic. Current is periodic and the average voltage is 0. For discontinuous conduction, always current is periodic. Current is periodic and V naught T average will again be 0. For discontinuous conduction, the current is periodic. If this current is periodic, then the average voltage will be 0. Okay? Is it fine, guys? I hope it is clear. So I told you about inductive load. Now let's come to the next thing. Now you have a current source. Okay? Now you have a constant current source, and don't look at this freewheeling diode. It's not necessary. Okay? Let's not look at the freewheeling diode first. It's a current source. So it's again simple. How to plot it? How to plot the wave shape? So again the wave shape is very simple. First you need to plot the. Now remember, the conduction is always continuous in this situation because the current source is there. If current source is there, conduction will always be continuous. Okay? You have to remember this. Conduction will always be continuous. There is no freewheeling diode in the first case. We are assuming that there is no freewheeling diode, and since there is a current source, if there is a current source, conduction will always be continuous. Okay? Just remember this point. So these are my phase voltages. These are my phase voltages. Okay, this is VAN, this is VBN, and this is VCN. Okay, these are my phase voltages, and now you can see that the current is always there. Current is always there. So continuous conduction will be applicable. So the average output voltage will always be. Average output voltage will always be 3√3 Vm by 2 pi cos alpha. Okay. This will be my average output voltage, always. This will be my average output voltage, okay? Because the conduction is always continuous. Current source is there, na? If current source is there, conduction will always be continuous. You don't need to worry about that, okay? And alpha, this will be my average output voltage. Now, what is the maximum alpha? What is the maximum alpha you can take? So the alpha max in this situation, it will be 180 degree. Because output voltage in constant current source situation is from positive max to negative min. Okay, so at alpha equal to 0, this is the positive max value, and if you take alpha equal to 180 degree, it will be maximum negative. So alpha max is 180 degree. Okay, remember this point. Alpha max is 180 degree. I hope it is clear to everyone. So if you have a constant current source, conduction will always be continuous. If conduction is always continuous, then average output voltage will remain like this. Okay, but if you take a freewheeling diode, then the situation will change. Then you can't take alpha greater than 150 degree. Why? Let's take a freewheeling diode and let's try to understand that. If you have a freewheeling diode, then output voltage can never be negative. Remember this point. Output voltage can never be negative. If you have a freewheeling diode, this is my current source, I naught, let's say, and you connect a freewheeling diode here. There is a freewheeling diode, okay? This voltage is VAN, this voltage is VBN, this voltage is VCN. Now I want to plot the output voltage wave shape. This is my V naught T. I want to plot the output voltage wave shape. So what we are going to do is, let's say this is T1, this is T2, and this is T3. and we want to plot the output voltage waveshape V naught T. So for that, what I need to do is I need to plot the phase voltages first. So this is the waveshape of the phase voltage. Okay, this is the waveshape of the phase voltages. Is it fine, guys? Tell me. This is VAN, this is VBN, and we have VCN. This is my VCN. Is it clear? So we have VN, VBN, VCN. Now what I'm going to do is I want to take alpha greater than 30 degree. Let's take alpha equal to 60 degree. Let's see. Alpha greater than 30 degree I want to take. Let's take alpha equal to 60 degree. Okay, if alpha equal to 60 degree, let's see what will be the wave shape, what will be the output voltage wave shape. So T1 should get fired at this instant, but we know that T1 will not get fired at this instant. The firing angle is 60 degree. So T1 will get fired at this instant. This is the instant of firing for T1. Now this is the instant of firing for T2. Okay, at this instant T2 will get fired. Okay, at this instant T3 will get fired. Fine. Now you can see that from this point to this point T1 should conduct. T1 should conduct. But can the output voltage be negative? No, sir. After this point freewheeling diode will conduct. It means output voltage will become 0. Okay. So you can see that this will be the wave shape of the output voltage. And then again VBN, and then it will remain 0, okay, and then it will be VCN. I hope it is clear. Okay, so this will be my output voltage wave shape. Is it clear? This will be the output voltage. Now it is not continuous. The wave shape is not, the output voltage wave shape is not continuous. So you can see that average output voltage will not be, now it will not be 3 root 3 Vm by 2 pi cos alpha. It is not correct answer. Why? Previously it was 3 root 3 Vm by 2 pi cos alpha, Vm by 2 pi cos alpha. It was previously it was like this. Average output voltage was like this. 3 root 3 Vm by 2 pi cos alpha. This was the average output voltage if there was no freewheeling diode. But now you have freewheeling diode. In case of freewheeling diode, if you take alpha beyond 30 degree, let's say take alpha equal to 30 degree, then output voltage will have a 0 voltage gap. If there is a 0 voltage gap, then this formula is not correct. Now which formula is correct? That resistor formula, if you remember, that resistance formula. In that resistance, if you remember this formula, the shape was same. In that case, you have this formula, na? 3 root 3 Vm by 2 pi 1 plus cos of pi by 6 plus alpha. Okay, so the same formula I have to use here. 3 root 3 Vm by 2 pi into 1 plus cos of pi by 6 plus alpha. Okay, this is the formula which I need to use for average output voltage, remember. But if alpha is less than 30 degree, then there is no need for freewheeling diode, because output voltage will never be negative. I mean, it will not be 0. Okay, it will never reach to the negative point if alpha is less than 30 degree. So there is no need for the freewheeling diode, and the conduction will remain continuous, and you can apply this formula. Okay, so please try to understand this. It's a very important point. I told you how to tackle this situation. And the average output voltage. Okay, so be careful whenever you have freewheeling diode, then what will happen, and if you don't have the freewheeling diode, what will happen. So I told you about the thyristor case. Now let's come to the RLE case. Okay, in RLE case, now it will be very complicated. So what you do is you replace it with a constant current source. You assume that the current is ripple free and replace it with a constant current source, and you can solve it. Okay, so I told you about the RLE also. Now let's come to 3-phase full wave controlled rectifier. Can I start, guys? Tell me everyone. So this is 3-phase full wave controlled rectifier. Now we will start this. So tell me, guys, are you getting all the points? Tell me everyone, are you getting all the points? So I told you about 3-phase half controlled rectifier. Okay, and now I'm entering in 3-phase full controlled rectifier. Okay, 3-phase full control rectifier. So those students who haven't liked this session, please like the session, guys. Please like it. Okay, so let's start this. So 3-phase controlled rectifier is this. Now in 3-phase controlled rectifier, you want break. Okay, let me give you a break. So the break is you can say, okay, tell me guys, you want break or can I continue? Tell me everyone, you want break or can I continue? Tell me everyone, you want break or can I continue the class? No problem, Raghuram. I think we can continue. Okay, let's continue. So now what I can have is, now we have the resistive load. First of all, please tell me, there are two groups. One is the upper group, one is the lower group. This is T1, T3, T5 and this is T2, T6, T4. Now if you look at this carefully, in upper group there should be one device that should be conducting, and the lower group also one device will conduct. Now the upper group is connected in common, look at this, the upper group is connected in common cathode configuration, their cathode is common, and the lower group is connected in common anode, their anode is common. You can see that here the anode is common, here the cathode is common. Fine. Whenever the devices are connected in common cathode, then the device which has the highest voltage on anode will be under forward blocking mode. Okay, whenever the devices are connected in common cathode configuration, the device which has highest voltage on anode will be under forward blocking mode. And whenever the devices are connected in common anode configuration, you can see that their anode is common, then the device which has the lowest voltage on its cathode will conduct, will be under forward blocking. Tell me guys, is it fine? Is it fine? Is it fine now? Tell me everyone. Okay. So now I want to check which one is under forward blocking mode and which one is under reverse blocking mode. Okay, to understand that I need to plot the phase voltages first. So let's plot the phase voltages, though the phase voltages are not important here. Okay, but anyway, let's plot the phase voltage and let's look at the device which is under forward blocking mode and which is under a reverse blocking mode. Wait a minute. This is VAN, this is VBN, this is VCN, again VAN, VBN. Okay, now we have these voltages, these are the phase voltages. Okay, these are the phase voltages we have. Now if you look at this carefully, from this point to this point, A has the highest voltage. So in the upper group you can see that T1 will be under forward blocking mode. From this point to this point, T1 will be under forward blocking mode. Now T2, not T2, T3 will be under forward, because B phase has the highest now, and B is connected to T3. In the upper group we are looking. So T3 will be under forward blocking mode, and now T4 will be under, T5 will be under forward blocking mode, because in the upper group T5 is connected with the phase C. Is it fine? So we have studied which one is under forward blocking mode during these ranges. It means T1 can start conducting at this point. You can fire T1 at this instant. You can fire T3 at this instant, and you can fire T5 at this instant. So these are the alpha 0 instant for T1, T3, T5. Now what about T2, T4, T6? Look at the highest negative. Highest negative. So under this range, you can see that which phase is lowest? B phase is lowest. B phase means T6. Okay, this is the T6 will be under forward blocking mode. Now during this range, which one has the lowest voltage? C phase. C phase means T2. T2 will be under forward blocking mode, and then T4, and then again T6. Okay, and then again T2. It means you can fire T6 at this instant, you can fire T2 at this instant, you can fire T4 at this instant, and you can fire T6 at this instant again. Okay, so these are the alpha equal to 0 instant for T2, T4, T6. Is it clear, guys? Is it clear? So we have checked what are those instants. What are those instants at which the thyristor can be fired? So you can see that every 60-degree interval you can change the thyristor name like this. At this instant you can fire T1. At this instant you can fire T2. At this instant you can fire T3. At this instant you can fire T4, T5, T6. Okay, I hope it is clear. So every 60-degree later, after every 60-degree, T1, T2, T3, T4, T5, T6, you can fire them. Okay, I hope it is clear. I told you this using this diagram, this phase voltage diagram. But let me tell you one more point, and that point is, let's say alpha is 0. Let's take alpha is 0. Alpha 0 means T1 will get fired at this instant, T2 will get fired at this instant. Between these two interval, between these two instants, you can say in the upper group T1 is conducting because T1 will get fired at this instant. No? And between the lower group, T6 is conducting. T6 conducting means B phase is there. Now tell me, T1 conducting means A phase is at the output. A phase is at the output, and T6 conduction means B phase is at the output. At this point you have B phase. It means the output voltage will be the line voltage, VA minus VB. It means at the output voltage, the line voltage will appear. Is it fine, guys? Tell me. First of all, have you understood this? It means the output voltage will be of line voltage. Output voltage will be line voltage. Now we have to look at the line voltage, not the phase voltage. So let's plot the line voltage. Let's plot the line voltage and don't look at the phase voltage. So I'm not interested in phase. Now I am interested in line voltage because output voltage will be the line voltage. So let's draw the line voltage first. How to draw the line voltage? Let me tell you the simple way to draw the line voltage. What you need to do is you need to make the triangles like this. So make the triangles like this, okay? These are the triangles. Make the triangles like this. And then you can make the triangles like this again. Once you draw these triangles, remember every triangle is of 60 degree. Once you draw this triangle, just add the caps like this. Add the caps like this. Okay? You can add the caps like this. I hope it is clear. Okay? Now, these are the line voltages. Now, draw the origin line. The origin line should be here. After 30 degree, you have to draw the origin line. After 30 degree, you have to draw the origin line. Why? Because you know that you have the phase voltage. Let's say this is VAN. this is VBN, and this is VCN. These are my phase voltages. Now what are the line voltages? If you draw the line voltages, you can see that this will be my VAN, this will be my VBN, and this will be my VCN. It will lead by 30 degree. Okay, whatever the VAN, this will be VAB, VBC. Wait a minute, I have done it wrong. These are the line voltages, guys. So I have to write them like VAB, VBC, and VCA. Okay, I have to write it like this. So I have plotted the line voltage, and the line voltage will lead by 30 degree from the phase voltage. Okay, now we can see that if this is VAB and this is VCA and this is VBC, what about this voltage? This is just opposite to that. It is VAC. Now if it is VAB, then the opposite to that is VBA, and this is VBC, opposite to that is VCB. Is it fine? If you look at the angle between these line voltages, this is 60 degree, this is also 60 degree, this is also 60, this is 60, this is 60, this is 60. So you can see that the angle between these voltages, these line voltages, is 60 degree, and there are 6 voltages. There are 6 line voltages: VAB, AC, BC, BA, CA, and CB. At every 60 degree interval, you have the line voltages. Now look at the first. Look at this wave. Look at this wave. This is the origin point, and it is leading by 30 degree. This wave is leading by 30 degree. So you can say that this is VAB. The first one is VAB. This first one is VAB. And the second one is VAC. And then VBC. And then VBA. And then VCA. Okay. And then VCB. And then VAB. Okay. This is again VAB. VAB. The same wave will repeat here. You can see that this is VAB. Now how to write them? How to write them? Because it's not, it's not easy to remember them. There is a way. And that way is, remember only the two, AB and AC. Okay. If you know this is AB, this is AC, then you have seen that the first subscript is repeated 2 times. Now you have to replace this A with B, because the sequence is ABC. If the first subscript has repeated twice, then change the subscript. Since here it is A, here also it is A, so you have to replace it with B. So now this voltage will become B here. Now look at the last subscript. The last subscript is B here, and now it is C, so you have to repeat it. Every subscript will repeat 2 times. Okay, every subscript will repeat 2 times. Now you can see that A has repeated twice, then you have to change A only. C will remain same. Okay. Now the last subscript has repeated twice, so C can be replaced with A in the sequence. C can be replaced with A. That's why the last subscript I have replaced with A, and the B will remain same. Now you can see that the front subscript, the first subscript has repeated B. So after B you have to take C. Okay. Then in place of B I have replaced it with C, and the last subscript is not repeated. Okay. Now you can see that the last subscript has repeated. So now I have to change the last subscript with B, and the first subscript I have to take same. Okay. So you can see that in every 60 degree interval, these are the 60 degree interval. Okay. These are the 60 degree interval. In every 60 degree interval, you have to change the voltages like this. So these are the line voltage. Now from where the alpha is measured, you can see that before AB, what was the voltage? Tell me guys. Before AB you have VCB, no? So this voltage is VCB. Now look at this instant. At this instant, CB has changed to AB. Now tell me which subscript I have changed? The first subscript. In place of C, you have A now. It means the first subscript has changed. Whenever the first subscript has changed, remember this upper point represents the first subscript, and this lower point represents the second subscript. Okay. Let's say the output voltage is VAB. AB means the upper subscript represents this point, the first subscript represent the upper point and the last subscript represent the lower point. Now if you look at this wave carefully, you can see that here you have CB and here you have AB. Now the last subscript remains the same, but the first subscript C is changing to A. Previously it was C. It means the phase C was connected here. Now C is replaced with A. It means previously T5 was conducting. That's why C was there. Now it is replaced with A. What does it mean? It means T1 get fired. T1 get fired. Then only A phase will appear here. Okay. So you can say that at this instant T1 will get fired. What about this instant? Tell me guys. What about this instant? Which thyristor get fired? Tell me which thyristor will get fired. At this instant, which thyristor will get fired? Tell me everyone. Tell me which thyristor will get fired at this instant. Look at the subscript. A is same, only the last subscript has changed from B to C. From B to C. If you look at this, previously it was B. It means T6 was there. T6 was conducting. That's why B phase was available here. Now you are replacing B with C. B with C. It means now T2 should fire because C is connected to T2. So now at this instant T2 will get fired. I hope it is clear. Okay. At this instant T3 will get fired. At this instant T4 will get fired. At this instant T5 will get fired. T6 and again T1. Okay. Again T1. I hope it is clear. Okay. You can use the subscript idea. Using the subscript, you can see which thyristor will get fired. And remember, this is for alpha equal to 0. It means if alpha equal to 0, then T1 will get fired here. So alpha 0 is measured from this point only. From this point, alpha is measured for T1. For T2, at this point, from this point onward, alpha is measured for T2. Okay, so remember the firing angle instant, the alpha instant, because alpha is important. Okay, you should know from where the alpha is measured for T1 and T2 and T3, T4, T5, T6. Okay, I hope it is clear. Okay, now I can proceed. I told you the wave shape of the output voltage, how the output voltage will look like. Okay, in three phase, if I take alpha equal to 0. Now let's take alpha greater than 0. If I take alpha, let's say 60 degree, if I take alpha equal to 60 degree, what will be the wave shape? If I take alpha equal to 60 degree in R load, what will be the wave shape? For alpha equal to 60 degree, T1 will not start here. T1 will start conducting from this point onward. T2 will start conducting from this point onward because delayed by 60 degree, na? Everything is delayed by 60 degree. Is it fine, guys? If I delay everything by 60 degree, then you can say that T1 will start conducting not at this point, at this point. Now VAB will be this voltage. VAB will be this voltage. And then VAC. Then T2 will start fire at this instant. Now this is VAC. Is it fine, guys? And then VBC. Please try to understand that. Okay. Try to understand that. Oh, wait a minute. What happened? It's not working. Okay. So now at this instant T1 will start. So this is VAB. And then at this instant T2 will start. So this is VAC. At this instant T3 will start. So this is VBC. Is it fine, guys? Tell me. Have you understood? So this blue color wave is the output voltage. This blue color is the output voltage. Is it clear, guys? Tell me. This blue color is the output voltage. This blue color is the output voltage. Is it fine, everyone? Tell me. Is it fine? So for alpha equal to 60 degree, this will be the output voltage wave shape. Now you can see that it is just continuous. There is no zero gap. There is no zero gap. So in resistive load, if alpha is less than 60 degree, the conduction will be continuous. Conduction will be continuous. Okay. For alpha equal to 60 degree, it is just continuous. You can see that the current will also be the same shape, na? Because it's a resistive load. In resistive load, whatever the voltage wave shape is, the current will also be the same. Okay. The current shape will also be like this. Only the magnitude will change. Only the magnitude will get reduced. The current will also be the same. So if alpha is less than 60 degree, then the current will also be continuous. Okay. There will be no 0 point. There will be no 0 point in current if alpha is less than 60 degree. Okay. And if alpha is equal to 60 degree, just continuous. And if you take alpha greater than 60 degree, conduction will be discontinuous. Discontinuous conduction. Okay. Now what will be the average output voltage? Let's calculate the average output voltage. What will be the average output voltage? If you want to calculate the average output voltage, V naught T average for continuous conduction or just continuous conduction, for these two cases, it will be 3√3 Vm by pi cos alpha. Only 2 is the difference. I mean, in the half wave rectifier there was 2 here. In the half controlled rectifier, if you remember, there was 2 here, 3√3 Vm by 2 pi cos alpha. But now 2 is replaced. Now we have pi only. 3√3 Vm by pi cos alpha. Is it fine? For continuous conduction, this will be the formula. For continuous conduction. For continuous conduction. Okay, this is the formula. Now what will happen for discontinuous conduction? If you increase alpha beyond 60 degree, what will happen? Let me draw the wave shape. Okay, let me draw the wave shape for alpha greater than 60 degree. If I take alpha greater than 60 degree, let's plot the wave shape first. Let's plot the wave shape first. So the wave shape will look like this. First you have to draw the triangles. First you have to draw the triangles. Only 3-4 triangles are enough. Don't waste your time. Okay, only 3-4 triangles are enough. So you just draw only 3-4 triangles, not more than that. Okay, and then you draw it like this. Okay, so these are the line voltages. Okay, and this is the origin line. This is the origin line. This is VAB. This is VAC. VBC. This is VBC. Now VBA. Okay. Before VAB, we have VCB. We have VCB. Okay. Now for alpha, let's say 90 degree I want to plot. For alpha equal to 90 degree I want to plot. What will be the wave shape for alpha equal to 90 degree? Load is resistive. What is the wave shape for alpha equal to 90 degree? How to plot that? So let's plot. Alpha is 90 degree. So alpha is measured from this instant. From this instant 90 degree away. So 90 degree is this. It means from this point to this point it is VAB. VAB. T1 will conduct only during this interval. Okay. What about T2? After VAB we have VAC. So this should be the starting point of VAC. But 90 degree, alpha is 90 degree. So at this point VAC will start. At this point VBC will start. Is it fine? So now you can see that the output voltage will be, output voltage can never be negative. Output voltage can never be negative because load is resistive. In resistive load, output voltage can never be negative. If the output voltage become negative, then the current will also become negative, and negative current is not possible. You can see that the negative current is not possible. Okay. So that's why the current has to be positive. Current has to be positive. So you can see that the voltage will not become negative. So after this point, it has to be 0. Is it fine? It has to be 0, and the conduction will become discontinuous. Is it clear, guys? Tell me. The conduction will become discontinuous. Is it clear, everyone? Tell me. So there is discontinuous conduction now. So for alpha greater than 60 degree, if you take alpha, now we have taken alpha 90. 90 is greater than 60 degree. So if you have taken alpha greater than 60 degree, conduction will become discontinuous and this formula will not be the correct formula. Now what should be the formula now? How to derive the formula? To derive the formula, what is the period of this wave? Tell me guys. The period is 60 degree again. You can see that this point and this point, the same wave repeat after this point. Na? So period is 60. So 1 upon pi by 3 into, we have to take the area from this point to this point. Now what is this point? Look, this point is pi by 6. This is 30 degree and this length is alpha. So pi by 6 plus alpha to this point, and this point is, what is this point? 60 plus 60 plus 60 is 120 plus 30, 150, 5 pi by 6. So I have calculated this area guys, this area I have calculated. The starting point, if you look at the starting point is this, and this starting point is pi by 6 is this point, pi by 6 plus alpha. This is my pi by 6 plus alpha, okay? So pi by 6 plus alpha to this point, this is 5 pi by 6. This point is 5 pi by 6, is it fine? This point is 5 pi by 6. Now what is the equation of this VAB? The equation of this VAB is root 3 Vm sine of omega t plus 30 degree. Is it clear guys? This will be my average voltage. Now you can calculate this. It will be 3 root 3 Vm by pi, and the integration of sine is minus cos. If you put the upper limit, it will become pi 1 plus cos of, if you put the lower limit, it will become 60 plus alpha. This will be my average output voltage now. This time the average output voltage will change in discontinuous conduction. This will not be the average output voltage. This will be the average output voltage in continuous conduction only. Now the conduction is not continuous. You can see that. For alpha equal to 90 degree, conduction is not continuous. So the average output voltage will be like this. Is it clear guys? Can I proceed? Okay, so I told you about this R load. Now you can have L load. In L load, you don't need to do any calculation now. Let's say the conduction is continuous. In continuous conduction, the average output voltage is, tell me, V0T average is equal to 3 root 3 Vm by pi cos alpha. This is my average output voltage for continuous conduction. This is my average output voltage. Now you can see that if alpha is less than negative, if alpha is less than 90 degree, this V0T average is positive. V0T average is positive. What does it mean? It means this current I0T will be rising and it will be aperiodic. So I0T will be aperiodic and rising. Aperiodic, continuous and rising. It's simple, okay? I0T will be, because V0T average is positive, na? Okay. For alpha less than 60 degree, how wave shape? Okay, less than 60 degree, you can draw it yourself, na? Because this is shifted on this side. For alpha less than 60 degree, you can shift it on this side. If you don't know how to draw the wave shape for alpha less than 60 degree, what you are doing, guys? Arun? It means look at your preparation. At this time, you should know what should be the wave shape for alpha less than 60 degree. It is just a revision. I'm not going to tell you everything, okay? So do it yourself. I mean, if you have not studied it, then it will be very difficult for you, okay? Because I am doing revision. I'm not telling you everything because there are lots of things. So please be careful. So I told you in this case, this is my average output voltage. Now you can see that if alpha is less than 90 degree, it is positive. It is positive. It means average output voltage is positive. If average output voltage is positive, then the current in the inductor, the voltage, average voltage across the inductor is positive. So the current will be periodic, aperiodic, rising and continuous. Now if alpha equal to 90 degree, what will happen, guys? If alpha equal to 90, this will become 0. Average voltage will become 0. V0T average will be 0. What does it mean? It means the current will be periodic. If the voltage across inductor, average voltage across inductor becomes 0, then this I0T will be periodic. It will become periodic. It will become periodic. I0T will be periodic and just continuous. And just continuous. Why? Because if you keep decreasing this, keep increasing this alpha from 0, till this point it was positive. At 90 degree, first time it is become 0. First time it becomes 0. So that's why I call this point as a just continuous point. Okay, and the average output voltage is 0. Now if you take alpha greater than 90 degree, what will happen? If alpha is greater than 90 degree, then what will happen? This formula is not correct now, because the conduction will become discontinuous now. So alpha JC came out to be 90 here. Okay, alpha JC came out to be 90 here. Now if alpha is greater than 90, conduction will be discontinuous. Discontinuous conduction. Discontinuous conduction. Conduction will be discontinuous. Okay, the conduction will be discontinuous. Now the conduction is discontinuous and it's periodic. In discontinuous, always periodic. If the conduction is periodic, V0T average will be 0. Because if the current through the inductor is periodic, then the average voltage across inductor will be 0. So that's why this waves, this condition for inductive load, you will see these type of things. Okay. Now let's move to the current source. Now you have a constant current source. Now tell me, whenever you have constant current source, it means the conduction is always continuous. Conduction is always continuous. It means V0T average will always be 3√3 Vm by pi cos alpha. Okay, it will always be like this. And alpha can be up to 180 degree. Alpha max can be up to 180 degree. 180 degree. In the previous case, in R load, if you look at this R load, alpha max can be up to 150 degree. Up to this point, you can increase alpha. Na? So alpha max can be up to 150 degree. You can see that from this point, alpha is measured, and you can increase up to this point. Alpha max can be 120 degree, not 150. In our case, alpha max can be 120 degree in resistive case, because alpha is measured from this, and you can increase alpha up to this point. So this length is 60 plus 60, 120. Alpha max is 120 degree. Is it fine? What is the value of beta in discontinuous conduction? Thirumal Sai, I think you have attended me, you have joined me just now. I have told you that beta in discontinuous conduction cannot be calculated. Okay, you cannot calculate. Yes, in inductor case you can calculate. In inductive load you can calculate that beta. There is no problem at all. In inductive case you can calculate that beta, but in case of RL load you can't calculate that beta, because then you have to apply Newton-Raphson method. Okay, numerical method you have to apply in RL or RLE load. Okay, but in case of pure inductor case you can calculate that beta. There is no problem. You have to draw the wave shape and you can calculate it. Let's take a wave shape. Let's try to plot for alpha greater than 90, and let's see how the average voltage is 0 and how to plot the how to calculate the beta. Okay, let's try to plot this wave. Let me plot the wave shape for pure inductive load, and let's calculate beta. Let's calculate beta. But you can't calculate beta for RL load or RLE load. For inductive load you can calculate that. Let me tell you how. Okay. Okay guys, so now what I can do is take alpha equal to greater than 90 I have to take. So greater than 90 you can take maybe 100 or maybe 120, whatever. Okay, let's take alpha equal to 100 degree, not 120. Let's take alpha equal to 100 degree. Now from this point alpha is measured. Now tell me the VAB voltage, from where this VAB will appear. From this point I have to go to 100 degree. Now this point is at 100 degree because this is 60 and this is 90. You just add 30 to it, it will become 90 here, and this will be 100. Okay, this is my alpha equal to 100 degree. From here it is 100 degree. Now at this point VAB will start. Okay, in inductor case, at this point VAB will start. Now tell me, from this point to this point inductor voltage is positive, so current will rise. If you want to plot the current wave will start from this point and it will rise, it will go to the maxima at this point. So since the current has developed now, so thyristor will keep conducting. If the same thyristor will keep conducting, then the output will also go negative up to this point, so that the current becomes zero. At this point the current becomes zero. Okay, so you can see that this is my starting point and this is the end point, and this is symmetric about this point. So you can calculate this side angle and the same angle will be on this side. Now how to calculate? First of all, this instant is, what is this instant? This instant is 150 degree. Now tell me about this angle. We know that this length is 100 and this length is 30 degrees, so this entire length is 130 degree. If this point is 130 and this is 150, so this length is 20 degree only. If it is 20, what about this length? This length will also be 20. So this instant will be, what about this instant guys? This instant will be 150 plus 20, that is 170. So you can say that the extinction angle is 170 degree. Okay. Now I don't know how many of you have understood it, because this is important. I mean, not that much important, but the point is you can calculate the extinction angle in case of pure inductor case. Okay, whenever you have pure inductor, you can calculate the extinction angle beta. Okay, now what we have is, we have a current source. Whenever you have a constant current source, it means the conduction will always be continuous, and the alpha min can be 0 and alpha max can be 180 degree, because in case of current source you can vary the voltage from maximum positive to maximum negative. Okay, so maximum positive will occur at alpha equal to 0 and maximum negative will occur at alpha equal to 180. So alpha max can be 180 degree here in this case. Okay, so you remember this point. Now how to plot the wave shape? It's simple, but there are some important terms about in this circuit. Let me tell you those important terms. So this is my, let me plot the line voltage first. These are the line voltages. Okay, okay, these are the line voltages guys. These are the line voltages. Then this is my origin line. Okay, and let's say this is VAB, this is VAC, this is VBC, this is VCB. Okay, and this is VBA, VCA, VCB. After VCB we have VAB. Okay, so these are the voltages. Now let's take alpha equal to 30 degree. Let's take alpha equal to 30 degree. Okay, now for alpha equal to 30 degree I need to plot the output voltage. I need to plot the output voltage for alpha equal to 30 degree. What will be the output voltage? Let's plot it. So alpha should start from here, na? It should be measured from here. It is 30 degree. It means VAB will start from this. It will start from this 30 degree beyond that. So it is VAB, and then after 60 degree VAC will start. At this instant VAC will start. Is it fine, guys? Tell me. Is it fine? Tell me, everyone. So this will be my output voltage for 30 degree. Okay. And it's continuous, you can see that. It will remain continuous always because the current source is there, na? So it will remain continuous always. So for alpha equal to 30 degree, this is my output voltage wave shape, the white color wave. This is my output voltage wave shape. Now the question is, what is this phase current, IA phase current, IAT? How to look at this IAT? Tell me, guys. How to plot this current, phase current, IAT? What should be the method to plot this phase current IAT? This current will be there only if this T1 and this is T1, T3, T5 and this is T2, T6, T4. I think this is the numbering. Okay, let me check the numbering. Numbering is correct. Okay, so now IA will be there if T1 and T4 are conducting, because you can see that A phase is connected to either T1 or T4. So IA will be there only if T1 is conducting or T4 is conducting. If T1 is conducting, IA will be positive. It will go like this. And if T4 is conducting, IA will be negative. It will come like this. The current will come like this. Okay. So whenever T1 is on, IAT will be positive. IAT will be positive. Whenever T4 is on, IAT will be negative. IAT will be negative. Now the question is, how to check when this T1 is on and when this T4 is on? How to check that? By using the subscript you can check. We know that whenever T1 is conducting, the first subscript is A, because the A phase is connected here. So the first subscript, whenever the first subscript is A, it means T1 is conducting. And whenever the last subscript is A, the second subscript is A, it means T4 is conducting. This phase is connected here. A phase is connected here. Whenever the last subscript is A, it means T4 is conducting. Whenever the first subscript is A, it means T1 is conducting. Now in this output voltage, I have to look at the subscript. Okay, I have to look at the subscript. Now you can see that during this range, the first subscript is A, and during this range also, the first subscript is A. From this point to this point, A subscript is there. Na? The first subscript is A. It means T1 will conduct. It means IA will be positive and equal to I naught. IA will be positive and equal to I naught. I hope it is clear. So if you want to plot the IA, then IA will be, let me plot the IA for you. Let me plot IAT. So IAT will be equal to, you can take these points down. Okay, so we have taken these points down. Okay, now you can see that. Now we can see that from this point to, this 60 degree and this 60 degree, A subscript is the first subscript. So IA will be positive. IA will be positive equal to I naught. Okay, A phase current will be positive. Now next 60 degree, you can see that there is no A, neither in first nor in the second. So the current will be 0. Neither T1 conducting nor T4 conducting. So current will be 0. Now from this point, this 60 degree, A phase is second subscript, and also here the A is second subscript. So now for next 120 degree, 60 plus 60, 120 degree, the current will be negative. The current will be negative. It is minus I naught. Is it clear, guys? Tell me. So it is plus I naught here, it is minus I naught here. Next 60 degree, it is again 0. And then for the next 60 degree, it is positive. Is it fine, guys? Tell me. Is it clear? Is it clear? So I told you how the wave shape of this IAT will look like. Similarly, you can plot the wave shape for BN. For IBN, for IB phase current, IBT, you look T3 and T6. If T3 is conducting, the current is positive, and if T6 is conducting, the current is negative. Now when this T3 is conducting, if the upper subscript is B, if the first subscript is B, because upper subscript represents the first subscript. If the first subscript is B, it means T3 is conducting. If the second subscript is B, it means T6 is conducting. So using this, you can see in the output voltage, when B is in the first subscript and when B is in the second subscript, and you can plot B. Or there is one more way. Once you have plotted IA, you can shift it by 120 degree, you will get IB, and you can advance it by 120 degree, you will get IC. Okay, this way also you can plot IA, IB and IC. I hope it is clear. Okay, let's proceed, guys. Now we have RLE load. Again, in RLE load, I will not going to make the entire analysis like we have done in single phase case. So in three phase case, whenever you have RLE load, for continuous conduction, the average voltage is 3√3 Vm by pi cos alpha. This will be my average output voltage for continuous conduction. For continuous conduction. For continuous conduction. And remember, for continuous conduction, there will be some alpha JC, beyond which this alpha will, if you are increasing alpha, and if you increased alpha beyond alpha JC, it will become discontinuous. This formula will not be correct. So this formula is correct only in continuous conduction, and if the conduction is continuous, this current will always be periodic because of R. Since R is there, current will be periodic. So average voltage across inductor will be 0. VLT average will be 0. So whatever the output average voltage is, that average voltage will be utilized in this E and R into I naught T average. R into I naught T average. So it will be utilized between these two, R and E, because VLT average is 0. So from here you can calculate I naught T average as I naught T average is equal to 3√3 Vm by pi cos alpha minus E upon R. Is it fine? This way you can calculate the average current. Now if you want to make alpha greater than 90, and if you want that the conduction remain continuous, if you want that for alpha greater than 90, the conduction remain continuous, it is not possible. Why it is not possible? Because E is of this polarity. With this polarity of E, you cannot make alpha greater than 90 degree. There will be some alpha JC. That alpha JC will be less than theta Z. We have already checked that. So if you want alpha greater than 90 degree, and if you want continuous conduction, you have to change this polarity of E. Then only it is possible. Okay. So if you change the polarity of E, like this, RLE, if you change the polarity like this, then for alpha greater than 90, it can be continuous conduction, and this formula is still valid. For continuous conduction, this formula is still valid. 3√3 Vm by pi cos alpha. Okay. 3√3 Vm by pi cos alpha. This formula is still valid, guys. For alpha 9, we know that for alpha greater than 90 degree, this will become negative. If it is negative, it means this output voltage is negative, and the current will always remain in this direction. Current can flow only in this direction. And if this output voltage become negative, so it will not absorb the power. This V0 into I0 will not be the absorbed power now, because this voltage has the opposite polarity now. It means this will deliver the power now. Okay. So if you want to deliver the power, from this side to this side, first you have to revert the polarity of E. Once you revert the polarity of E, then you can increase alpha beyond 90 degree. Now in this formula, you can increase alpha beyond 90 degree, and this average output voltage will become negative, and now you can revert the power flow. I hope it is clear in RLE load. Okay. So now this is LE load. So do it yourself. LE load, it is not that much important, so I'm not covering it. Again, RE load, I'm not covering it, and I have covered the current source case. Okay. So that current source case I have already covered because that was important. Okay. So I think let's stop it here. So I have covered almost all the things which are important for your exam in phase controlled rectifier. Okay, so I have covered only two chapters. One is basics of power electronics and the second one is phase controlled rectifier, because it's a lengthy chapter. Now the remaining part is DC-DC converter and inverter. So I will arrange some more classes on DC-DC converter and inverter, maybe within a week or maybe within 4 or 5 days. I will arrange some extra classes, and in those classes I will cover that part. I will take some 2-3 hours class, and in that class I will cover the remaining part of the session. Okay, so Rahul Sharma, sir, sorry to disturb you, but sir 30-40 मार्क्स ही रहे हैं टेस्ट में, 30-40 मार्क्स ही रहे हैं, कुछ बताइए कैसे रिवीजन करें. राहुल शर्मा, प्लीज लुक एट योर मिस्टेक्स. ओके, out of these 35 to 40 marks, I mean, how much questions you are attempting? What is your attempt? Like 60 marks attempt or 70 marks attempt, and how many mistakes you are doing, and what type of mistakes you are doing? That is important. Let's say you are doing calculation mistake. It means your practice is not good. Okay, if you are doing conceptual mistake, you don't know how to apply, how to approach this question, then you have to understand the concept. Okay, if you are not applying the concept, if your concept is poor, if you are not able to think about the question, what should I how should I approach this question, what should be the method, if you are thinking like that, then you have to go with your concept. But if you are doing calculation mistakes, let's say there are 10 questions which you have made wrong because of the calculation mistake, then you can improve that by doing practice. So you can improve your score by doing more practice. If you are slow, let's say some questions are left behind because the time was not there, because you were very slow. If you are slow, then attempt 2 marks question first. Okay, then attempt 2 mark question first, then go to the 1 mark question. Because if you are slow, then better attempt the higher marks question. That will make you that will be more scoreable. Okay, so better you attempt 2 mark question first. So this way you can. Yes sir, calculation mistake ज़्यादा हो रहे हैं. अगर कैलकुलेशन मिस्टेक ज्यादा हो रहे हैं राहुल, देन व्हाट यू नीड टू डू इज यू नीड टू डू मोर प्रैक्टिस एंड यू नीड टू बी फोकस्ड, because it might be possible that sometime while you are performing the exam, then you start thinking some other maybe your mind go to some other place. Okay, it might be, it is natural, it happens to everyone. But what you need to do is you need to do more practice, you have to give more tests, and slowly your calculation will improve. Okay, slowly, just look at your mistakes and be truthful to yourself at least. Okay, tell yourself the true things, that this is wrong, I am doing this type of mistakes, why I am doing this type of mistake, next time I'll not do this type of mistake. So you have to be careful like this, and I hope that your marks will improve. Okay, at least get some 60-70 marks na, double marks you have to get, then you will be safe. Okay sir, फ्यूचर का सोचकर बहुत डर लग रहा है. फ्यूचर का मत सोचो यार, ठीक है, फ्यूचर में कुछ नहीं है अभी तो. कौन सा अटेम्प्ट है आपका, विच अटेम्प्ट इज देयर? राहुल शर्मा, टेल मी, आपका कौन सा अटेम्प्ट है? Thank you Lord, this session is more useful. Yes, in this session I have covered all the phase controlled rectifier. Okay, not the entire power electronics, but phase controlled rectifier I have covered. Okay, and let me tell you guys, I have told you the important points of the phase controlled rectifier, not everything. Okay, because as per the exam is concerned. Okay, so as per the exam, whatever the important topics are, I have covered all this. So your third attempt is there. Now if this is your third attempt, then you should attempt at least 70 na yaar. What you are doing, tell me what you are doing. If this is your third attempt, then your preparation should be good. Tell me guys, what you are doing. Third attempt, it means you are preparing for last 3 years. लास्ट 3 साल से आप प्रिपेयर कर रहे हो. लास्ट 3 साल में तो यार ऐसे हो जाता है कि सब कुछ याद हो जाता है. ठीक है, लास्ट 3 साल से बहुत ज्यादा होता है यार, पता नहीं आपने क्या किया है. बट एनीवे, डोंट फील बैड. द थिंग इज, कोई बात नहीं, ज्यादा से ज्यादा प्रैक्टिस कीजिए, डरना बंद कीजिए. पेरेंट्स को भी थोड़ा बोल दीजिए कि भाई तैयारी ठीक है बट किस्मत का कुछ पता नहीं. सो उनको थोड़ा कॉन्फिडेंस में लीजिए, एंड आई होप इट विल हेल्प यू. ओके, सो थोड़ा पेरेंट्स को भी थोड़ा सा उनमें लीजिए, क्योंकि डर असल में पेरेंट्स से ही आता है. आपको लगता है कि एक्सपेक्टेशंस हैं आपसे कि भाई योर पेरेंट्स वर एक्सपेक्टिंग फ्रॉम यू, एंड दैट्स व्हाई यू फील वेरी प्रेशराइज्ड. ओके, सो आप उनको बोलिए कि ये सिचुएशन है, क्लियर बता दीजिए, सच बता दीजिए, एंड देन यू विल फील गुड. ओके, एंड डोंट फील बैड. होता है, फेलियर होते हैं लाइफ में, सो आप फेलियर से भी ना डरे, बट पेरेंट्स को जरूर बताइए एक बार, बिकॉज देन आप थोड़ा लाइट फील करेंगे. ओके, ये बहुत जरूरी है. ओके, एंड उसके बाद स्कोर पे भी आपको फर्क पड़ेगा, आप देखिएगा, बिकॉज जब आप एग्जाम देने जाते हो तो स्कोर में भी आपका जब डर खत्म होगा तो आप अच्छा अटेम्प्ट कर पाओगे. सो दैट्स द इंपॉर्टेंट थिंग. ओके, पेरेंट्स नहीं है तो कोई बात नहीं, फिर आपको जो भी आपको लगता है कि भाई मेरे साथ ये परेशानी है, जिनसे भी डर लगता है, आपको कुछ तो डर लग रहा होगा ना, कहीं से तो पैसा आ रहा होगा, कहीं से तो आपका पास मनी आ रहा होगा, वो लोग एक्सपेक्ट कर रहे होंगे ना आपसे कि दिस टाइम यू विल बी क्वालिफाइड एंड दिस टाइम यू विल गेट गुड रैंक एंड यू विल बी सिलेक्टेड इन PSUs और सिलेक्टेड इन IITs. सो जो भी आपसे एक्सपेक्ट कर रहे हैं उनको बोलिए सो दैट आपको एक रिलैक्स फील हो. दैट इज मोर इंपॉर्टेंट. ओके, सो डोंट वरी, आई मीन परेशान मत होइए एंड अपने आप पे भरोसा कीजिए. कभी कभी हमें ऐसा लगता है कि हमें कुछ याद नहीं है, बट द थिंग इज, रियलिटी इज, whenever you start solving the question, automatically you'll strike, I mean the formulas will strike and everything will strike and you can easily solve them. So जब भी आपको लगता है कि आपको कम पता है, आप भूल रहे हो, तो आप अपने ऊपर भरोसा रखिए, परेशान मत होइए. डोंट बी प्रेशराइज्ड. ओके, और प्रेशराइज होके मिलेगा भी क्या, आप ये सोचिए, परेशान होके मिलेगा भी क्या इस टाइम पे. ठीक है, सो बेटर बी कूल. ओके, एंड परेशान मत होइए, बस अपने पे भरोसा कीजिए, मिस्टेक्स को कम कीजिए, स्पीड को थोड़ा बढ़ाइए, 2 नंबर के क्वेश्चन जल्दी पहले कीजिए. आई होप इट विल हेल्प यू एंड इट विल improve your marks. Okay, so tell me guys, let's stop the class here. Let's stop the class. So I will take 2 or 3 more sessions on power electronics, and in those sessions I'll cover DC-DC converter and inverter. Okay, so let's stop it here. Thank you for your interest and thank you for attending this class. Take care and bye. See you in some other session. Thank you.